good morning, or if you're tuning in from different time zones, good afternoon, good evening to you all. I'm super excited today to welcome you all to the inaugural Embodied AI Summit. My name is Ramana Kompella, and I'm a Cisco Fellow and Head of Cisco Research. At Cisco Research, we conduct research on emerging technology areas of strategic interest to Cisco, such as AI, ML, quantum, networking, and security, and so on and so forth. So we at Cisco Research have been conducting several research summits, including our biannual quantum summit that some of you may have attended. Today, of course, our focus is on embodied AI, or Jensen calls it physical AI, which is really the next frontier of AI/ML innovation. And we have an amazing program for you over the next 5 hours. We start with a fireside chat between Vijoy and DJ, two Cisco leaders I really admire. They've been driving substantial innovation around AI ML tech over the past several years now. And we are also pleased to have a fantastic lineup of talks from some of the best researchers and industry practitioners in the field. And these sessions are moderated by my team members and fellow researchers, Gaowen, Charles, and Jayant, who have actually been pretty active in the embodied AI space and have been pushing the state of the art in this area. Finally, we have a panel session around some of the foundational challenges associated with embodied AI and to make embodied AI practical and impactful for everyone. And so to keep it interactive, we are happy to have a Q&A channel. And this is actually hosted via Slido. So you should be able to click the QR code and you should be able to post a question, and our moderators will actually continue to monitor and pick up these questions as you post them for our speakers to be able to answer. I apologize in advance if we cannot get to all the questions because we have a compact schedule and a lot of ground to cover. So with that, let's kickstart the first part of the program, and which is a fireside chat between Vijoy and DJ. So just a quick intro. So Vijoy Pandey is the SVP GM of Outshift, which is the incubation arm of Cisco. It is responsible for bringing new products around new technologies, new personas, new markets. And the current goals for Outshift is to drive two internets. One is the Internet of Agents, which is leading into Internet of Cognition, and the other one is the quantum internet. And some amazing foundational and futuristic work is happening in Vijoy's org, embodied AI being actually another emerging frontier of research and innovation. And it's also my pleasure to introduce DJ Sampath, who's actually the SVP GM of AI software and platforms for Cisco. He's a visionary leader leading the charge in shaping a unified AI vision across the company's AI portfolio with a lot of innovative products such as AI Canvas, AI Defense, Defense Claw, and several others. Without further ado, I will pass it over to Vijoy and DJ for this exciting fireside chat. Over to you, Vijoy.
Thank you, Ramana, and welcome, DJ. Welcome everyone to the inaugural Embodied AI Summit, as Ramana said. We hope this series will continue, and we hope that it'll be more successful than what we've seen in the quantum side, because quantum has actually been a pretty successful series of summits for us at Cisco Research, and Embodied is the next frontier that we're trying to tackle. And with that, I would like DJ to introduce himself. But as you introduce yourself, DJ, one other thing I would like to ask you is, a little birdie told me that there is an embodied AI personality in your house as well. So give us a little bit of a flavor of your role as well as that personality that sits in your house.
You bet. First of all, thank you so much for having me, guys. And embodied AI is something that I care about a lot. But before I do that, let me give you a quick introduction. I'm your classic cliched immigrant. I came to this country almost about 30 years ago. $800 in my pocket, dreams of conquering the world, and ended up getting a PhD in computer engineering. And when I was doing that one of the things that was super interesting was I was working on, as part of my dissertation, I was working on building communication protocols for drones. Right. So my connection to like things that autonomously moved from one place to the other started back when I was working with the military, and it was a fascinating experience trying to define how these drones can communicate, how can you do waypointing with them, and a lot of these were being used in command and control situations where you had very little infrastructure available to be able to get them to do things, and it was a matter of life and death and making sure that these things communicated the right data at the right time, back to the home base. So it was a fascinating experience going through that arc before going down the path of the dark side, as the academics would call, moving into the industry, doing startups, and here I am. But at Cisco, my goal has been to fundamentally reimagine how we think about applying AI to a lot of different problems that we're solving. Thinking about agents, how agents work, and most recently trying to bring the entire platform together in a cohesive way that allows us to be able to solve very meaningful problems for our customers. Now, talking about what the birdie told you, yes, the birdie was right. As soon as, and this was a little while ago, before the tariffs kicked in, I wanted to make sure that I got my hands on one of the Unitary robots, the G1. It's in my garage. It used to be here in this room for a while before my wife requested that I lock it, in a separate compartment inside of the garage, because it's fascinating. It's one of the most interesting things about embodied AI is it's actually you can't reason about it just based on slides. You have to get your hands on it. You have to start playing around with these things, because you suddenly start to realize all of those attributes of like, hey, what does latency mean? What do the failure modes mean? How do these actuators work? Like, what does it take to be able to get it to perform a task? How do you teach it trajectories? It was really fun, and one of the most interesting anecdotes I was just telling you about was the UX of robots is super important to get right. What was interesting was the minute that we powered on, me and my son, we were working on this. He was super excited. He thought that we had a C3PO at home. It kind of was true. But when we powered on the Unitary robot, all of the motors start to get actuated when it tries to stabilize, and the gyros start to stabilize. And the robot just snaps up, and it scared the hell out of a 10-year-old who went back screaming, going, "Oh my God, it's alive! It's alive!" And it took a few extra cycles to get him to get a lot more comfortable. But no, it's actually fascinating to have hands-on experience of working with some of the modern machines that are absolutely incredible.
Yeah, actually, that brings me to like the first question here, which is actually let's take it in a twofold manner. One is, it almost seems like some parts of the robotic ecosystem are pretty far out and very well developed, and then there are some parts which are like still there's a lot to be done. And this is why we are having the summit, and there's a whole bunch of researchers here. There are really hard problems to solve in this space. But just let's start with your thought process. One of the things was, yeah, there are tariffs kicking in, and you wanted to get a Unity at home. But are there any use cases you had in mind for this Unity, or it was just getting your hands dirty and playing with this
I think
beast?
I think it's a good, it's totally that the last. I don't think it was like, hey, trying to get it to fold laundry is obviously one of my top missions, and that's sort of how, every single day you got to sit down and do this thing, and I think the complexity involved in trying to get it to be able to do that. I think there's just still a huge gap between the demo works versus it's actually useful inside of my house, and you don't quite understand that gap unless you start to live with one, right? When you live with an embodied AI, by the way, I've got a Matic robot that is, that cleans, my floors, and it's the first one that has a very similar type of, Tesla-like, vision for like, hey, where are obstacles? It creates an entire map of your home, and when you take a look at that model, it's very different from like any of the vacuum robots that we've had before, because they're starting to use vision to be able to fundamentally, do wayfinding. And the Matic robot is like a full generation above like anything else that we've seen, come out so far. So it's not just one robot. There are at least like 3 or 4 more. And obviously a lot of us have Teslas, which is one of the largest robots that we have, from an autonomous driving perspective. And I think there are some use cases that have been cracked open really, really well. But when we start to talk about like, the classic, humanoid type of robot, I think, inside of our households, I think there's still a long way to go for it to be, for you to sort of feel like it's safe and it's the right, types of things. So when I think about hey, what would I use it for? What is my killer app of starting to use something like an embodied AI? I think it's I still think it's going to make its presence be felt inside of like warehouses first. Like if you think about it, it's already, if you take a look at an Amazon warehouse, the amount of like robots that are out there is just, shocking when you realize how far they have leaned into using robotics to be able to do these things. And I think you're going to start to see that sort of like arc, go through the same thing as cloud. I think you're going to start to see the enterprises, pick it up in different ways, whether it is racking and stacking, in data centers, whether it is, humanoids starting to appear inside of like, putting things away, like, inside of, inside of a factory, inside of like an enterprise environment, plugging things, unplugging things. You're going to see autonomous, embodied AI doing security stuff. Like I still remember, I'm sure you know this from your time at Google. Every time, I would go to visit, there would be this robot that just is going around in your parking lots, from a security perspective. And so enterprises are more likely to do that adoption before it finally enters the home. So I think the arc is going to be, warehouses first, like large industrial warehouses, enterprises next, and then you're going to start to see it show up in home. At least that's my take, because the regulatory, the safety requirements, all of that stuff is going to have to kick in before we can, things become safe for consumers.
Yeah, I mean, including the UX, like you pointed out earlier. There's a lot of work that needs to be done.
That's exactly right. Yeah.
So if you think about Cisco's, like the places where Cisco plays and the markets that Cisco serves, data centers is a big market for us. Networking, we are a networking company. You mentioned Google. One of the things that we've seen back in Google, and Ramana seen this as well. Some of the fabrics that Google builds and the other hyperscalers build are just massive. And cabling and getting those cables right is actually a
Yeah.
pretty hard problem.
Oh,
And if you get it wrong, then debugging that is an even harder problem.
that's right.
And so getting robotic embodied AI in those areas to get cabling right, or being able to even debug remotely, because it's not a software thing that you can log in and debug remotely. So having something there, embodied AI there to help debug some of those things, are probably some of the first use cases that we'll have access to, and then move from there, as you said, on the arc towards enterprises. Any other use cases that come to mind when it comes to Cisco and where Cisco can play with embodied?
I think there's so much of the way I think about this is that one of the interesting things I learned about almost about 5 years ago is that there's an operating mode that's called the lights out operations, right? And first time I heard it, I was curious, hey, what does that mean? And it turns out, like, and this is again speaking with one of my friends in the intelligence community. They were talking about how when they do these overnight views of like factories, sometimes they're looking for, hey, are there people inside of factories in remote locations and whatnot. So what is fascinating was when they talk about lights out operations, they discover these factories which are completely dark, but at the same time they detect a lot of activities that are happening, but there are no heat signatures that match with that of a human. So it tells you that, hey, the factory is fully active and there are no humans, but there are no lights, which tells you that that is a factory that's entirely powered by robots, right? When you start to think about that for a second, there are a lot of the fundamental assumptions that we have made of like the things that we have built for humans that won't hold true. But now you open up an aperture for like being able to solve problems that you've never solved before. So I think what's going to happen is when you start to think about the lights out operations for a data center, like you pointed out, racking and stacking, being able to do cable verification, being able to do like, hey, hot aisle inspection, like being able to see where do you need a little bit of extra cooling, I think it's going to be a very core part of like how we reimagine the fabric, right? When you start to think about, hey, I have to go back and replace all of my cell towers with like the networking equipment inside of a closet. I have to look into the retail back rooms. I have to, reimagine what my Wi-Fi access point looks like. I mean, it's very hard to have a person constantly walking around trying to, measure the wireless signals and attenuation properties and then keep updating them. But hang on a second, a robot can do that tirelessly and over again and make sure that your Wi-Fi hotspots are constantly being reallocated. When you start to think about, again, from a security perspective, I think, today we've got Meraki cameras that are constantly looking at things, from from a security perspective, from an environmental monitoring. We've got sensors, we've got badge verifications, and all of a sudden, you can now start to see how all of those start to evolve into physical security use cases. From a supply chain perspective, if you think about this, there's so much of things that we're building that requires robotics to to be able to like effectively inspect, hey, are we getting the right types of things? Are we locking them in, from like testing to like validating all of these things? I think there's a massive set of use cases that make sense for Cisco, and more specifically, the way I almost always think about this is, every robot is a node in a network, right? And every node needs, identity. Every node needs policy. Every node needs fundamentally a network that allows you to be able to connect across the board. So this is not a new business for Cisco, right? It's another Tuesday for us.
Yeah, I mean, so one of the use cases that you pointed out earlier was Wi-Fi hotspots and what's happening there. And we are working with Cisco IT to do like a really simple demo here, which is you go to a Cisco Live and you run into these hotspots and you don't know where it's happening and how it's happening. And instead of sending a person around, like you said, to check out what could be wrong,
Yeah,
a robot might be wandering the show floor, figuring out where the hotspots are and where they are missing. And I think that's an incredible use case
I love it.
for embodied AI, where you're not wasting somebody's time. They're just drinking coffee and
No,
making sure that an embodied AI is actually figuring out networking problems for you.
that's right. That's an awesome use case. I would totally want one of those in every conference and every meeting room. Popping a robot in there.
Yeah, so switching gears a little bit, because we were talking about Cisco's strengths and Cisco's right to play in this space. If you think about robotic control and you think about the many loops that a robot runs, they're running at different frequencies, they're running in different time cycles. So you have navigation, you have the actuators, you have the collision avoidance, but then there's also the planning and the conversations and the reasoning part of it. And that's where it gets really interesting from the research perspective, because there are different types of models, some that might be sitting within the embodied AI, some might be sitting in the cloud. They need to connect to each other. You have the VLA models that might be split between the embodied as well as the cloud. So there's a lot of architecture here that needs to be solved for before we can even commercialize this. And I keep Ramana and I keep joking that we're still solving the blueberry sorting problem, but there's a lot more to go beyond that. There's a lot for Cisco to do, and you were starting to touch upon this, but there are networking issues, there are of course security issues and observability issues that we already talked about.
That's right.
But they're like we've heard that networking problems are a big deal. There are edge compute problems that might be a big deal. So can you touch a little bit upon some of those aspects?
No, absolutely. Like, I'll tell you a quick personal anecdote, right? I got a tour of a robotics factory. My NDA prevents me from telling you which robotics factory in California, um, that I visited. I can't tell you that it was actually a company that used to be a car manufacturer and still is a car manufacturer that has stopped a few productions of their cars. But what I can tell you is this, right? What was really fascinating was, they had these robots, and these robots were lined up, and they were lined up in, both like, in rows and columns. And each one of these robots, actually, you had like, humans training these robots by performing the same action over and over again. And so they were collecting all of these traces to be able to get these robots to be able to perform. And by the way, these were a long line, like about, almost about 20 horizontally, robots, and about 50 vertically inside of that. And so it's a lot. It was a massive sight to see. If you watch the movie I, Robot, this is one of those scenes from that. But what was really interesting was that every single robot, in addition to just having a tether, had a drop a wire that was connecting and a bunch of cables that were going through it. So I automatically assumed that, hey, that's probably power. Turns out it wasn't just power, and a big part of it was having wired network drops into the robots. And what was fascinating was that the biggest problem that they talked about was like, hey, listen, it's so hard to be able to get all of these robots on the Wi-Fi and like have the right kind of signal, because when the connection drops and the packet drops happen, the telemetry doesn't necessarily go back, and so it causes a whole lot of coordination issues when you don't have the right type of network that's powering a fleet of robots. And so to me, that was like a big aha moment, that just the light bulb moment just that went off, which is we are completely underestimating, like when we start to bring in, robots into our workforce, into our day-to-day lives, the kind of demands that it's going to have on like core basic infrastructure is going to be fundamentally different. And then when you add to that, what the point that you were making about, robotic control, when you start to think about, the loop frequency the interesting thing is this, right? When you start adding like things like reasoning, task planning, like multi robot coordination, it's humans, we do this intrinsically because we observe signals and we react slightly differently when another person is in the room. You create a sense of space, and different cultures have different sense of space, and it gets very interesting. And it's like just the coordination across the board is going to be something that requires a massive rethinking in terms of edge infrastructure. How do we think about, from a Cisco's perspective, what does low latency networking really mean? How do we start to think about fast path and slow path? I think the equivalent of that, thinking about the fast loop and the slow loop for like collision avoidance, or like for balance, like compared to like learning modules that can happen slowly to be able to think about things. I think there's a very interesting set of problems and use cases which make a lot of sense for Cisco. When we start to think about, identity and policy, I think it's going to be a big deal. Every robot is going to need an identity of like, hey, who does it belong to? Is it acting on behalf of somebody? Is it acting on behalf of itself to be able to perform a task? Because every action is going to need a policy. I mean, it was a good thing that Asimov set up like some rules for us to be able to follow, but you need to still be able to enforce those policies, right? You got to be able to say, hey, listen, here's how we think about agentic trust. Extended to zero trust, extended to atoms, to physical things, because we've always done this for the cyberplane. We think about, I'm responsible for a product called AI Defense, which allows you to be able to secure agents and like, prevent the agents from being attacked. We think about the world as, say, protect the world from agents, protect the agents from the world. It now starts to apply very realistically for robots. Like, you got to protect the robots from the world, and you got to protect the world from the robots. And so it's going to be a very interesting set of use cases that Cisco, is going to find itself smack dab in the middle of. Observability is obvious. You can't operate a fleet if you can't see what that fleet is doing, right? At the end of the day. And so when you start to think about, hey, can we have a thousandized product for our robots? I think it's going to be a real thing, where you need to know the connectivity of every single robot at any given point in time. And last but not the least, I mean, you got to think about, the agentic control plane that you all have been building inside of Outshift. As you think about like, hey, what are the gateway patterns? What are the communication patterns? How do the robots communicate? Like, they don't need to like talk to each other, say hi, hello in English language. They can communicate with each other in completely different protocols that they can make up on the fly. So I think there's so much of things that we deeply care about, and it's our bet is not on the robot itself. Our bet is on the fact that there are going to be 10 million robots that need the same things that 10 billion devices already need from us today, right? And whether it's a network, whether it's an identity, whether it's a policy, it's just that we're going to inject a brand new thing that says, hey, don't fall on grandma. That is a new policy that you're going to put in there, so that the robots don't keel over and fall on grandma. I think that's going to be the difference.
I think don't fall over DJ or Vijoy is also one of the rules that I'll put in there. But
hey man, you're a tall person, like I think you'll be fine when a small 5 foot 180 pound robot falls over you. I think you'll be able to kick it away.
I hope AI defense prevents that from happening. But I know we're coming up on time, but we are all big believers in agentic software. We're all big believers in where the world is headed with LLMs, and where we're going with multi-agent software and multi-agent systems. And I know you're a big believer, but extending that out to physical AI and embodied AI, what do you think is the end goal here? I mean, what do you think is the future? What are you most excited about in terms of, if we do get to embodied AI in a good way with better UX, better control loops, better VLAs, and better observability and networking and security? what's possible that excites you?
I think the thing is our imagination has not yet fully comprehended the kinds of amazing things that you could achieve. I think we're a lot of times our human imagination is constrained by the things that we see and we understand. I'll give you the example. Like, there was this fundamental notion that cars driving themselves was like an esoteric idea about 30 years ago or 20 years ago. Growing up, we thought the cars would fly, cars would do things, but it seemed too fantastic. And today, when we drive, when we sit inside of these self-driving cars, it's such an it's such a normal thing. The moment that I got my mom and dad, used to self-driving, it was a big chasm. Like, you could see them be fundamentally shocked, that, wait a minute, it does such a good job. It was a little ironic when they actually, said that it drives better than you, and they meant it in earnestness. And I was like, okay, yeah, that's cool. So I think what we're about to sort of like see with with embodied AI is like there are problems that we haven't really quite thought through. A lot of the human labor condition, that has created an asymmetry in the current modern macro world is going to go through like a complete upheaval. And I think what's going to happen is, labor, just like how tokens became like, an indication of intelligence, embodied AI is going to fundamentally change the economics of labor, physical labor, which means you're going to now have the opportunity to sort of have things that you could never have before, and solve for problems that you could never solve before. Like, there's a massive problem that's emerging as a population ages. Being able to support them in a meaningful way has always been a massive challenge that I think you can resolve. Like, you can solve this very meaningfully. I think you're going to start to see, situations which involve physical harm, humans going into a hazardous environment to be able to go out and solve for problems. You now have an amazing alternative to be able to do that. Providing, reducing the risk to a firefighter, is like a top, use case that you're going to start to see this be used. I think embodied AI is going to find its way in like very, very meaningful shapes and forms, that is going to ultimately improve the quality of life. I know that there's going to be the obvious argument of like, oh, it's going to take away our jobs, and there's going to be this robotic uprising. But I think there's always a positive and negative side to this, and I think the positive side will overwhelmingly be higher from an advantage perspective, and it's upon us, like the researchers on this call, like folks like yourselves that are thinking about this problem deeply, to be able to say, hey, how are we going to build systems that are going to fundamentally improve humanity? And I think it's in our hands to be able to make that happen, so which I think is super exciting.
That is an amazing picture that you're painting there, DJ. It's fascinating and it's hopeful, and it's something that we should all shoot for. But there are like some really large problems between where your head is at and the utopian world that you paint and the reality, the ground reality today. And that's what, like you said, the researchers on this call and the work that they're all doing is to bridge that gap and bridge it quickly, because we're all waiting for this to happen in our lifetimes. And I'm not even going to wait for that long, maybe in the next 2 to 3 or 4 years. So thank you for being with us, DJ, and thank you for this fascinating conversation and those examples. They really resonated, and for painting this amazing picture for what the future might look like. So,
hey, thank you for having me, Vijoy, Ramana. Really appreciate you both, and I'm excited. I'm going to tune in. I'm going to listen into the rest of the conversation. But this is fascinating, and thanks for doing this.
thank you, Ramana. Back to you.
Wow. Thank you. Thank you, Vijoy and DJ, for such an insightful session. It's an amazing fireside chat. With that warm up, I know we are racing against time, so we should now switch to the presentations part of the program. I can't wait to listen to all these amazing talks. So over to you, Gaowen, to lead the first session. Yeah, please take it over.
Thank you, Ramana. Good morning, good afternoon, good evening, everyone. Welcome to Cisco Research Embodied AI Summit. My name is Gaowen Liu, and I'm a researcher from Cisco Research. I'm very happy to chair this session. We have a fantastic lineup of speakers. I'll briefly introduce each speaker before their talk. Our first speaker is Bolei Zhou, Associate Professor in the Computer Science Department at UCLA, where he directs the Vision and Autonomy Intelligence Lab. Please welcome Professor Bolei Zhou.
Hi, can you hear me? Great. Yeah. First of all, I would like to thank Cisco Research, Ramana and Gaowen for inviting me to join this online seminar. So it's quite inspiring. Also, DJ share a lot of insight on the embodied AI. So I'm Bolei, so I'm associate professor at UCLA. Today, I would like to briefly introduce our research on enable and scaling embodied AI for sidewalk autonomy. So as DJ shared that autonomous driving, right, is everywhere. So everybody can use the app and take a autonomous driving drive, right? So a lot of companies working on this area. I would say autonomous driving is also robot navigation in urban environment. But besides autonomous driving, there is another side of robot navigation. So here, this is a video I captured last month at the LA. You can see here is a small size robot. So this is a food delivery bot from Robotics. So it's a startup doing the food deliveries for Uber Eats and DoorDash. Now you can see this robot is running on the sidewalk. The sidewalk is actually very challenging. You can see people walking around, a lot of obstacles over there. Unfortunately, for those bots, they are many human teleoperated, which means there is some human sitting behind and teleoperate the bot to overcome the challenging sidewalk situations, right? So I would say you can see here we have many companies right now running the business, like the startup. They are running a fleet of robots on the sidewalk for the food delivery task. Also, there are many other mobile robots on sidewalk, such as electric wheelchairs, disabled and elder people using the wheelchairs moving around on sidewalk. Also, in the future, you can see the robot dog and the humanoid, if they can really happen, right? So they will not run on the road. They will also walk on the sidewalk. They will also interact with human beings, right? So in the case, you can see the sidewalk navigation is actually very challenging. So here is a video captured by the food delivery bot. So this gives you the first-person view how challenging the sidewalk navigation is. You can see here we have a lot of obstacles, parked scooters, right? So the robot try to navigate on the sidewalk. Also, we have the robot running in the real world, right? The weather. A lot of different weather conditions, right? This is raining, and we also have the cars on the driveway, right? And also different lighting conditions, right? The robot have to do the food delivery like in the evening most of the time, right? People order the food in the evening, right? The bots have to navigate on the sidewalk in different lighting and weather conditions. Also, there are a lot of interesting activities going on. You can see here, last video showed there is a dog just laying on the ground, and the robot have to maneuver very, very delicately to avoid a step on the tail of the dog, and also try to avoid the collision with the people and a lot of obstacles. Right? So you can see that the embodied AI for sidewalk navigation is a very important task, right? It's also very promising business surrounding this, right? Ranging from the food delivery bots to electric wheelchairs to all the in the future, like the robots, robot dog, and the humanoid. But right now we have this current sidewalks, right? So sidewalk is really unpredictable, and also the task is a long horizon task, which means the robot have to navigate 1 or 2 miles to reach the destinations, right? To overcome all the unpredictable and the challenging conditions. So over recent years, people start putting a lot of effort try to tackle the sidewalk autonomy. Many people tackle these problems through imitation learning, right? So we can collect a lot of videos, like those robots are teleoperated by humans. Then we can design deep neural network, like end-to-end models, also borrow some methodologies from autonomous driving areas to build this navigation foundation models. So there are many navigation foundation models have been built, and my lab also have built some of the models. So for the model details, so I just keep for now. But you can see different labs build different models and also different companies running the board on the sidewalk. So one very important issue for now is how can we evaluate and ensure the safety of this autopilot model on the sidewalk, right? So sidewalk is mainly designed for human beings, right? Right now we try to deploy the boards on sidewalk, right? So how can we ensure the safety? So in the case, the simulation become very important. So we want to thoroughly evaluate the autopilot models in simulations and so a lot of corner cases to the bots before the real world deployment. Over the years, people have been developing a lot of simulations, right? So for autonomous driving, like we have a Kala, and also for in household environment, we have iGibsons. But there are many limitations for the existing simulations, right? So for example, iGibson and Kalas, they have rich scene context, but their simulation efficiency is very low. And also on the other hand, NVIDIA have been pioneering this GPU accelerated simulation, such as the Isaac Lab and the Isaac Sim. One limitation for the GPU accelerated simulation is that they have very high simulation efficiency, but they lack the rich scene context, right? So because originally those simulations are built for the locomotion or manipulation task, where there are only limited number of objects the robot can interact with, right? So right now we want to build a simulation for the urban robot, right? So in urban environments, we have so many different objects. So to push the effort, last year we released urban simulators called the Urban Sim, built on top of NVIDIA Isaac Sim. Now you can see here we can simulate all kinds of robots, urban robots running in the urban environment, like from the food delivery bot to humanoid bot and to the wheelchairs. Then you can see here we have a humanoid running into the trash, right? So we try to avoid that. Then we want to build the simulations to test other cases. So one key design for the urban thing is that we want to support the parallel evaluation and the parallel trainings. So previously, the NVIDIA Isaac Sim only have this simple simulation, which means they can parallelize the simulation, but each simulation can only have limited number of objects. They have the uniform environment. But here to support the urban simulation, where each urban simulation environment have a different set of objects. So we develop some method called asynchronized scene sampling that allow us to sample different set of objects that we can simulate in the environment. So here is the demo video showing you that we evaluate the bots in different simulation environments in urban scene, and we further use simulation to do the poster training for our navigation foundation model for different bots. Still, from the simulations, we have high sample efficiency, but you will notice that the visual appearance is still not so ideal. So the next problem we try to address is for the scene to real gap, right? Because the simulations have not only this graphical appearance, which far from the real world RGB input, right? To tackle the issues, we leverage the recent progress in computer vision, like 3D reconstructions, to create the digital twins and the digital cousins from the real world videos. For example, here is a work called the V2 Sim. Then this semester can take a video as an input. Then we can reconstruct the simulated environments from the videos. Then it become interactive. Then we can put this reconstruct the environment into the simulation and put our bots into the training. Because this is a simulation, data-driven simulation, is very high, has a very high sample efficiency. Then we can train the bots with reinforcement learning. Now you can see here the bot is running to avoid the collisions. Because the simulation have a very realistic visual appearance, then we can directly deploy the bots in the real world through this kind of zero-shot scene-to-real transfer. Right, so this video thing behind is a Gaussian spanning technology, right? So we put some constraint with the depth and the normal surface as a constraint to improve the geometric consistency of the reconstructions. We also include many dynamic object like 3D assets inside the Gaussian spanning environments to improve the interactivities and the training efficiency for the bot. Right. So we open source this V2 Scene to the public. So the community already using the V2 Scene to reconstruct their environments from videos. But there are still limitations for the V2 Scene because right now, giving one video, right? So we only can create one digital twin of the environment. So it's not that efficient, right? So you have to collect a lot of videos in order to get many environments. More ideal case will be like giving this one video. How can we create multiple variants of the simulations that we can run our agent? So here I call this kind of digital variant as a digital cousins for the original video. So we want to create multiple digital cousins as a simulation environment to train our bots. So how can we achieve the digital cousin creations? So here is a recent work we published at the iClear last month called Urbanverse. So right now on one side, we have this real world videos. On the side, we have the simulations. Instead of directly using Gaussian spanning to reconstruct, we can actually get some intermediate abstract representation of the scene from the real world videos. So here we extract the 3D scene layout of the scenes from the real world videos. So we will indicate the concepts such as the different cars and trees and their layout and their spatial relations. So then we can utilize this scene graph or scene layout as the intermediate representation, then put different 3D assets into the environment. Then we can create a variation of simulation environments with different 3D object instances. Then after we have so many different training environments, then we can start user environments to evaluate our autopilot models. So this demo video is showing you that we are running this pre-trained autopilot models in the simulation environment, right? You can see the simulation environment is more like a word model that can help us evaluate the capabilities of the models before the real world deployment. So after this simulation testings, we have this real world testings, right? So the bots, we thoroughly evaluate that, then the bots can start running in the real world. So this is another work we have. The model we developed have been like pre-trained on real world videos and evaluated in the simulation, then we deploy in the real world. So this is the bots running autonomously on sidewalk and try to follow the lane and try to avoid collisions with people. Then we also have many work on this cross embodiment deployment, right? So the models we trained on the wheeled robots. So we do this transfer learning, then we can deploy for other robots. Here is a unitary lagged robots running in the urban environment, try to navigate around on the sidewalk. Not only the unitaries, we also evaluate the model on many other embodiments, like from the wheeled robot to the wheel-lagged robot from deep robotics. We also deploy our model for this assistive wheelchairs. You can see here, we not only we can deliver the food, we can also deliver the people autonomously to certain locations in the environment. Okay, so you can see here in the future, right? So we will have a lot of robots running in the urban environment and interact with each other and also interact with peoples, right? So we really want to like embrace the future of connected robots. I think it's a great opportunities for Cisco as a AI infrastructure companies to support this kind of future of a connected robot. Okay, so I will stop here. So let me know if you have any questions.
Thank you, Bolei, for the insightful talk. We have several questions from the audience. So the first question is, which problem do you think is harder, sidewalk autonomy or autonomous driving, since sidewalk robots operating at a much slower speed? So what's the key difference between these two technology?
Yeah, that's a great question. So for the sidewalk robots, you can see we have people like walking on the sidewalk, right? So people is very unpredictable, and some pedestrians really want to interact with a robot. So how can we solve this human-robot interaction problem is one of the challenges. Another challenge is these resource constraints. Like for the full-size cars, you can store a lot of LiDAR, a lot of cameras, and then the car have a strong powers. But for this small-sized robots, it's really hard to put a lot of like sensing device. So right now, the camera we have is just a monocular RGB camera. It's even very hard to put a LiDAR camera there, right? So then we want to solve the sidewalk navigation from this monocular single RGB camera. So that is another very challenging problems here.
I see. So you mean in this use case, you have less sensors and limited resources, and so edge and efficient computing will become very important, right?
Yes.
I see. We have another question. What's the split between what the robot is natively doing versus where the human comes into the loop in your Coco robot food delivery space?
Yeah, so so for the delivery case, so right now those bots are being teleoperated most of the time by humans. So right now we want to include this the autopilot. You not use the autopilot to fully replace human because we are not getting there yet. So here we want to implement a paradigm of human AI shared control. So shared control means human robots control the robot together, like remotely or on the edge device, such that maybe the AI can operate the bot like 80% of the time or 90% of the time. The human teleoperator will be more like a safety operator standby and watch the AI operation and take over the controls when some accident or some risky situations happens. So this kind of a human intervention can be further used to improve the AI autopilot model. It's actually very similar to this Tesla. You know, when you engage autopilot, then something may happen. Human will take control. Then those intervention is being uploaded to Tesla clusters, then further to fine-tuning their model, right? So in a case, the human factor is very important that we can continuously improve the model performance.
I think we have one more question. How much inference is done at the edge versus in the cloud?
So right now, most of the computing is done on the edge device. We try to push more on the edge device because you know the connectivities in this open world settings is very fragile, right? So right now we may have AT&T and T-Mobile is two modems, but the connectivity is still not good enough. So we want to push more on the edge device. So in that case, when the robot lose the signal, still can operate in the environment.
Yeah, I think that's a good use case for on edge device deployment. And thank you again for the talk and for the engaging question and answer. We really appreciate it. Yeah. We will move on to our next speaker, Chris Xiaoxuan Lu. Chris Xiaoxuan Lu is an associate professor in robotics and AI at University College London, where he directs the robotics and multimodal AI lab. Please welcome Professor Lu.
Okay, thanks for having me here. Gaowen, can you see my screen?
Yes,
Great.
I can see.
All right, let's get started. Hello, everyone. I'm Chris from UCLA, and it's a great pleasure to be here. Attending the summit, and the Fireside talk was great. Was so inspired. Well, today I want to talk about vision language action models, or VLAs in short. This will, be a more perspective talk than a technical talk, so that we may ignite the discussion later. One motivation behind this talk is that recent success of large language model and vision language model makes it very tempting to think that connecting these models to robot action give us a straightforward path to general purpose robots, right? But actually, once intelligence enters the physical world, the problem changes a lot. To see why I say so and understand where we are now with VLAs, I guess it's useful to go back a little bit to the movie Rex paradox, which was coined in the 1980s by several AI pioneers. Well, their observation back now by then is very interesting. They somehow found that tasks humans consider intellectually difficult, like logic, math, chess coding, can be relatively tractable for machines. But since humans do effortlessly, like moving, grasping, adjusting grip, recovering from sleeps, remain extremely hard for AI. Well, the reason behind is like physical intelligence has enormous complexity if you consider how many loops inside a physical execution by a robot, right? And this paradox underpins the whole universal rule for robotic system design till today. In the last few years, we made impressive progress on the first half of the Moravec paradox. LMs and VLMs showed that reasoning-like capability can really scale. And the central idea behind is often captured by the scaling law. Namely, we add compute, data, model capacity. Then the test laws follows a predictable power law trend. Such a trend turned many difficult digital tasks, coding, visual understanding, and document generation, into engineering problem of scale. So there's a playbook somehow. Collect massive data, train large models, evaluate on a shared benchmarks, then steady improvement is expected. But the question here is that can VLA models really follow the same playbook? Well, before answering that, let me first have this slide. This slide somehow shows the current VLA recipe, which mirrors somehow the above playbook, but at the action training for robotics. So the pipeline essentially has three training phases. The first training phase, models start from the internet scale text, image, video pre-training, which gives a semantic and visual understanding. Not surprised. Second, they add cross-embodiment robot data, often mixing the famous data sets like OpenX embodiment, as well as some high-quality, high-fidelity simulation data to map representations into the action space across robots, across tasks. Last but not least, these pre-trained models are fine-tuned in the local environment with a small number of human demonstrations, sometimes from 20 to 40 episodes. And we hope these models adapt reliably to the target task and scenario. Well, this pipeline looks elegant, but does it scale in robotics the same way it scaled for language and vision? To me, the answer is not directly. To understand why I say so, let's first take some time to see what a VLA model looks like inside. Well, a representative example I take here is Pi 0.5 from the Physical Intelligence, which is a pioneer company in this domain. Well, it has three main parts. A vision encoder that turns camera images into visual tokens, a VLM backbone that combines image tokens, language prompts, and robot states, such as drawing angles, right? Of course, we need to have an action expert in the end that converts the features from the VLM into the future action tokens, including joint and grip comments, which can be executed by the robot. Well, this is a very natural design from a VLM perspective, right? We reuse a powerful vision language model and attach an action output head. But it also reveals a deep assumption we made here. The robot is just treated as another output modality besides images and text. But does this kind of design mindset really work in the practice? Sometimes yes, but these models can also be very fragile in practice. Here I show 3 failure demos I randomly searched a week ago, actually. All these kinds of demos coming from VOA style systems in the real settings, including a tape picking failure, a close folding failure, a bottle grasping failure because of the instruction following error. Well, the important point here I want to say is like, this kind of cases are not strange corner cases compared to autonomous driving car, right? They are ordinary manipulation tasks. Yeah, small changes in object pose, contact, material, clutter, lighting, or even scene setup can make the policy fail completely. Its failure suggests a big thing. Real models is somehow limited by the very weak generalization, even under mild distribution shift. This kind of generalizing concern is also evidenced by recent findings. So on the left of the slides, the authors from the Lirong Pro team showed that even for a simple manipulation tasks, success rate can collapse very quickly when the initial positions of the setting change or the perturbations happen. And on the right, our team did some quick linear probing experiments to probe the model representation capability. As a model goes through the 3-phase training pipeline, as I mentioned before, the VLM features in that model becomes progressively less expressive on the generic visual understanding tasks. Well, it actually matters a lot because robotics needs to be both specialization and generalization, right? That's ideal robotics we want to have. We want models to become good at actions, but not by losing the broader visual grounding or understanding capabilities that make the VLM useful in the first place. So that's why I feel like the playbook here starts to diverge. The LM and the VLM recipe worked because the world was digital, data was already abundant online, outputs were reversible, and held out benchmarks were often good enough to guide the development progress. Robotics somehow breaks these assumptions. A robot doesn't just produce a token answer, right? It acts, and that action changes the world around it. So the challenge here is no longer only about finding a better VLM model architecture or smarter algorithm. It becomes a full-stack system problem to me. And here, let me briefly unpack 3 bottlenecks around that system design, including data, execution, and evaluation. So the one comes first is data, which is also the most important one in my view. The simplest way to put it is like, you can't scrape action. But for LLMs and VLMs, the internet somehow gives us enormous observational data. Text, images, videos, captions, and documents, they're passive online. But robotics needs interventional data. What happens when a particular robot acts in a certain scenario? For the example of manipulation, this key signal is not just about video frame. It includes action history, joint angles, gripper state, pause, maybe talk, and the environment's response for sure, right? But most of the signals are missing from the internet video. A YouTube video of someone folding a shirt may show the outcome, but not the high fidelity or very fine-grained force, grip adjustment, joint states, or even the recovery strategy, right? Well, some advanced techniques like UMI-style systems, high-fidelity simulation, or world models can help bridge the gap a bit. But to me, none of them removes the need of the real-world data. That comes with a second bottleneck about the execution. Well, in a chatbot, token generation is a final product. If the model is wrong, the user edits the text, regenerates, or early stop it, right? Nothing wrong there. But for robotics, generation is only the beginning of the physical consequence. A generated action changes the world. One failure may be final, like a collision, a dropped object, a broken tool, or unsafe motion by the robot itself, right? There's also a latency trap. Many modern AI systems rely on slow syncing on purpose, such as verification or multi-step planning. But physics doesn't pause while the model syncs, especially on mobile robots when they carried with limited compute and poor connectivity to the cloud. Finally, there's also a bottleneck about evaluation, which is often got ignored. Well, for digital AI, benchmarks were imperfect, but they give the field a shared target. ImageNet structured very well the progress in vision, language and coding. They also have very good benchmarks that help the areas to advance in the same way. Robotics doesn't yet have an equivalent. We don't have a true physical ImageNet. Instead, we often rely on isolated demonstrations, including my lab, actually. Let's say one app, one robot, one setup, one task distribution, and many hidden engineering choices, right? This makes the whole process very difficult to replicate. And what is missing is actually a shared physical evaluation arena or infra that tests most models across tasks, maybe scenes, perturbations, or even hardware differences in practice, right? It would be also very important to maybe log why failure happens, right? In this way, evaluation becomes not only a leaderboard, but part of the learning infra itself. Well, so since this three bottlenecks, let me now very briefly share two stepping stones from our groups. Well, the first one targets the data bottleneck. Our motivation is inspired by the fact that today, many robots and development sites were already fine-tuning VLAs locally using their own collected embodied experience, namely the training phase 3 in my previous slide. Much of that local fine-tuning data is effectively used just once, then got wasted or deleted. Each site improved its kind of own model, but the pre-trained global VLA model they pulled from the first place doesn't necessarily learn from this local adaptation experience. So our idea is to treat this local fine-tuning process as a feedback channel to the pre-trained. So each client collects embodied experience in its own environment and fine-tunes locally. But instead of sending the raw data back to the central server, the client only shares the model updates akin to the federated learning spirits, if you know this area. And then the global VLA model can aggregate these updates and benefit from many local adaptation experience without having the raw data centrally stored. Does it work? Well, this slide shows some preliminary results using Path 0.5 with that idea. I want to be careful here because this is still ongoing work. So I would frame it as an early proof of concept rather than a solved problem. Anyway, we compare three settings on a liberal benchmark. First, the local fine-tuning. Each client trains only on its own local data with no aggregation. Well, this performs very poorly, as expected, right? Because each client only sees a Lirong slice of the task distribution. Second, we have centralized training. Here, all data is pulled together, giving us the upper bound setting somehow. This is very good in accuracy, but it requires sharing the raw embodied data, which can be storage expensive if you consider the video demonstration we need here, and sometimes privacy sensitive for many home scenarios. Lastly, we have the federated version of that. Each client fine-tunes locally, then only the model updates got aggregated. No raw data shared in this process. Though not perfect, this idea has a sign of life, and the performance reached around 90% success rate overall. I guess the key message here is not like, federated learning or Fed average is the final answer, but is that collective VLA improvement is feasible and was taken seriously. Another example here to make my point more intuitive, maybe. We train 5 clients. Each client contributes one cubed stacking task with a specific color combination. So no single client sees a full stack task space. Then after federated learning, we tested the shared VLA model on a new instruction. Here is a put the orange cube on top of the blue cube. Its combination was not directly learned by any individual client, if you see the videos here. And on the bottom left, the federated trained model succeeds actually very well in this unseen scenario, while the baseline kind of trained model without this kind of aggregation falls back to a previously seen combination that essentially implies overfitting after the local fine-tuning. And the second stepping stone I'll briefly talk is about execution reality. Well, the motivation is simple. Many VLA systems benefit from the reasoning traces that decompose a task into plans, subtasks, movements, visible objects maybe, and previous states. But standard embodied chunk thoughts like e-code can be very slow. This is very important because even a good plan is less useful if it arrives too late for control, right? In our example, standard E-code takes around 5 seconds per step, which is too slow for many manipulation tasks. At Acura this year, we proposed a fast E-code. The idea is very simple. This basically, not every part of the reasoning trace needs to be regenerated every time. So stable thoughts can be cached, while changing thoughts are updated more frequently. Importantly, this method doesn't require retraining of the model. Here is a simple demo to show the banana picking task comparing the standard E-code and our fast E-code system. Well, in the bottom, our fast E-code system keeps the reasoning structure and the quality very well, but schedules the computation more efficiently. So the stable thoughts are cached, changing thoughts are updated, and action decoding proceeds in an asynchronous way. Well, on the top, the standard E-code, which is still generating, is too long. I guess I want to wait for it. It regenerates a full reasoning trace every time. It works, but it's super slow, right? All right, I guess that's 2 stepping stones I showed here. But they are not very technical here, but this kind of the example I want to advocate for the system level VOA work we may need. To wrap up, I guess the challenges around the VOAs remain substantial, but so as the opportunities, right? In my view, future VOAs shouldn't be expected to be trained once and deployed everywhere. They should continuously improve through the distributed embodied experience, where robots learn from interaction, updates flow across systems, evaluation anchors reality, and the generalization becomes very collective, right? That is the embodied AI flywheel we need. And building that will require AI researchers, infrastructure builders, and industry partners to work together. Right, that's it. Thanks. I'm happy to take questions now. Gaowen.
Thanks, Chris. It was a great presentation. We still have time for maybe one or two questions. The first question is, given VLA's robustness issues and fragility with respect to environment conditions, should we abandon VLA completely and move forward to other models like world models? Do you think there is a merit in continuing to increase robustness of VLA using strategies like federated VLA?
Is it one question or two questions? Because I feel like it's two parts of the question. One part is about
one question.
Is the VLA the right direction?
Yeah. The first
okay.
question.
I'll take it one by one. Yeah,
the first one is, do you believe VLA is the correct model? And I think
that's a great question, actually. And as a person starting from a SLAM field and moving to this field, I do see the future or the promising paths of the VLAs, right? There are many settings for robots, which is a great part of that. I guess if we just narrow our kind of minds to the, specialization stream of the robots, let's say if you want just to pack a box in a factory, maybe you don't need a VLA, right? But to me, that sector is, is very narrow compared to the very broad opportunity space, maybe in everyday home, like the domestic settings or home settings, which go into the concept or underpins the concept of the generalist robots, where you interact with the robots with natural language, and the robots is expected to do the tasks beyond or extrapolate what they have learned. We need the generalization in that space. I think world model can somehow help this stream. I don't think world model idea essentially conflicts with the VLAs, right? Many works combine the two together. But even for world models, I'm not an expert there, so I won't pretend to be. But to me, if world models cannot benefit from the real world, maybe world model will really work for maybe 3D games or in the digital space. I have no doubts there. But for a robot which requires centimeter or millimeter precision, when the grip moves, I actually have strong doubts. I am a strong believer real world data is needed. Of course, simulation data is also important, right? A second part for the federated learning. Well, I think there's a main bottleneck here compared to like first talk. I really want to advocate the importance of data. But for now, unless you hire people to collect this kind of 100 million data from teleoperations or that, I don't find other ways. But the point is like a community like Robots or Hugging Face, they do have this kind of researchers collecting their data to fine tune. So why not, utilizing them? I think to me, it's clear answer there. Yeah, that's it.
We still have other questions, but to stay on schedule, we have to move on to the other speaker. Thank you again, Chris, for your great presentation. And
Okay.
our
Thank you,
next
God.
speaker, thank you. Our next speaker is Shubham Tulsiani, assistant professor at Carnegie Mellon University in Robotics Institute and a member of the Computer Vision Group. Welcome, Professor Shubham Tulsiani.
Yeah, thanks a lot, Gaowen, for the introduction. Am I audible and the screen visible?
Yeah, we can see your screen.
Okay, great. Yeah, thanks for having me over. It's a pleasure being here. I'm Shubham, and today I'll take this opportunity to talk to you about some of the research that our group has been doing through the lens of this somewhat philosophical question of whether we need 3D for robotics. Okay. So I actually come from a computer vision background, and for a while in my PhD and partly in my group at CMU, we've been focusing on the vision question of, hey, how do we build systems that can understand the spatial structure of what they see? So, for example, the holy grail would be we have systems that can take images or videos and have almost a 3D replica that you could act in of the world that they see, right? And this is sort of a pretty broad goal, and more specifically towards this goal, we have had works that could do 3D or 4D reconstruction, for example, taking a few images of an object or a scene, inferring the geometry and structure of that scene, inferring the dynamics of the objects if things are moving. This reconstruction problem really only focuses on reconstructing what's visible. And so if we want more complete representations of what we see that even model the missing regions, we've tied in works that also do generative 3D or recently generative 4D modeling to infer more complete representations from visual input. And we've also focused a bit specifically on being able to reconstruct, predict, understand these interactions that humans are doing in 3D. For example, you can look at a video of someone pouring something from a bowl, understand what that means in 3D space, for example. Okay. So that's, I think, one part of what our group focuses on, but not what I want to focus on today. The other part of what our group focuses on, perhaps more relevant to the discussion today, is we want to lay the stepping stones for generalist agents that can work out of the box. So for example, this Rosie robot from the Jetson, robots like these that you could just bring home, unbox, and ask them to do meaningful things in new environments, perhaps new tasks, right? And given these two focuses of our group, one very natural question that I keep asking myself is, what's the role of the stuff we are doing on the left of the slide to aid the stuff that we're trying to do on the right of the slide? So in particular, what's the role of being able to have a spatial understanding of the underlying world for robotics? Sort of rephrased in a different way, do we need 3D representations or 3D related inductive biases for solving robotics? Okay, and that's sort of the question at a high philosophical level that I want to focus on in today's talk. Okay. And I think a good starting point for examining any such question, if we want our answer to stand the test of time, is to really look back at the bitter lesson that Rich Sutton said the community learned. And if any of you have not read this blog from, I guess, 7 years back now, I would really encourage you to go and search for this. It's a really nice read, but I'll give you a high-level summary of this. So I think Rich Sutton, a few years back, was looking at the progress in the field over many decades, taking, I think, chess and language modeling as an example. And in chess, the early systems that we built really tried to leverage how humans play chess. And similarly, in language, the early models we were building used concepts like parse trees, etc., to understand things. And then Rich Sutton's observation was that, okay, the methods that really stood the test of time, for example, search and deep reinforcement learning in chess, or just using really large models trained with lots and lots of data in language, those were the methods that effectively leveraged computation for these problems, that scaled the use of computation as much as possible for these problems. So, for example, for chess, deep reinforcement learning, where agents played chess against themselves and taught themselves, really leveraged computation. Lots of computations for solving chess, and similarly, the large-scale models learned with large-scale data could effectively leverage computation for solving problems in NLP. And his lesson that he wants the field to take away was that we should really build methods that leverage computation effectively. And a word of caution was that whenever we try to incorporate human knowledge for such systems, it tends to complicate things that makes them less general, and we should be wary of doing that. So, taking into account the bitter lesson for the question that I've asked below about 3D representations, one possible corollary that I think the field largely assumes is that moving forward in, span of multiple years, we really shouldn't be using 3D for robotics, or approaches that use this human inductive bias for 3D representations in the middle, will not stand the test of time, and that from the bitter lesson, perhaps that's a corollary that we should take away. I would argue this is a common belief of some of the researchers in the field. For example, if we look at the predominant approaches for policy learning, which is one of the canonical tasks in robotics, where given some input X, which could be a perception, etc., some goal specification, which could be something like language, the agent is supposed to output actions that it's supposed to take to achieve this goal given the current observation, right? Or if we look at the other canonical task in robotics, which is world modeling, where the agent is supposed to predict the next state of the world or the next observations that it would see as it acts or moves in the world. For both of these tasks, I think the current approaches that the community is building really builds on the hypothesis that large-scale data and models are all we need. So, for example, VLAs that we looked at in detail in Chris's talk, just scale data and sort of models for learning policies, or for example, the typical world models that we learn through typical tools in generative modeling rely on these transformers trained end-to-end, and none of these have any 3D biases or 3D representations in the middle. But in our group, I think I'd say we are taking a different bet, and we're making sort of the conjecture that this corollary of the bitter lesson that we don't need 3D for robotics is not really correct. And in fact, there are ways we can leverage 3D-based mechanisms, even in the era of large-scale modeling, large-scale data, to improve robot learning. And I'll just try to walk you through some of these use cases at a high level, and that there are still many different roles that 3D can play for solving robotics or for building systems that have physical intelligence. And I think one of these roles, perhaps the most commonly adopted one, is that 3D can serve as a structural bottleneck. For example, and this is based on one of the recent work from our groups, Text4D, which you're welcome to look at if you are interested in more details. But in this case, 3D can serve as a shared language that different modules use to talk to each other. In our case, something like a planner and a policy. So to be more concrete, in this work, we were looking at dexterous manipulation. So we wanted a multi-fingered robot hand to be able to do some tasks in the real world. And as Chris's talk also highlighted, collecting data for training such things is a huge bottleneck. Collecting robotic data, especially for dexterous manipulation through teleoperation, is a big ask. So the approach that we took was to have a generalizable planner, which was a composition of a video generation model and the 4D reconstruction line of work that I briefly alluded to earlier. So here, this video that you're seeing is not a real video, it's a generated video. So given an image, the model knows that the task to be performed is to place this object at the specific location. We can query a video generation model and then reconstruct it to lift this understanding to 3D or actually 4D, because we're also modeling how points change over time. And then we could give this plan, which is essentially these 3D point tracks of the scene, to a task-agnostic policy that doesn't really care about language. All it cares about is it sees some 3D points, it knows how it wants to move those 3D points, and this combination lets us do sort of zero-shot deployment to the real world. So in fact, this robot that you're seeing picking up an object and perhaps later it will pour stuff from a different object, has not seen any real-world robot data. The planner has seen lots and lots of real-world data through this sort of video generation. The policy did not see any real-world data, but through 3D being this shared language that these use to talk to each other, we could get around this and do essentially zero-shot sim to real, where the policy was only trained in simulation, but through this generalizable planner that was giving the policy instructions in the 3D space, it could adapt to the real. Okay, so that's sort of one specific use case of 3D for physical intelligence. One other possible role that 3D can play is to guide computation in our end-to-end systems. So for example, hopefully we're all aware of this architecture called transformers, which are really the building block across all of the models that we see these days. So if you've used ChatGPT, or if you've used any video generation model, image generation model, image reasoning model, the computational backbone for such models is a transformer, which has this scale dot product attention mechanism where multiple tokens sort of talk to each other to update themselves. Okay, and in a recent work, we were looking at designing transformers for multi-view input. So for instance, if you have a robot in a workspace and there are 3 cameras looking at that robot, different tokens of the visual input correspond to different patches of different images. Okay, and so if we want to have a sort of computational block for processing such multi-view input, it really benefits the model to understand that each token really corresponds to an array. And so you can use this information to design slightly modified attention mechanisms that respect the geometry of the input. Okay? And once you do this, you can get significantly improved sort of plug and replace attention layers that you could use for many different tasks that require multi-view input. So here is showing this for sort of a video generation or view synthesis example, where on the left is a previous attention mechanism that doesn't use geometry, and on the right is our attention mechanism that does use geometry in some way. And this is a mechanism that could be incorporated anytime you have multi-view inputs, a robot operating in a workspace where there are multiple cameras, or world modeling, generation, etc., etc. Okay, so it's just, having some 3D information in this computation mechanism could let you have sort of a much more accurate computation mechanism. And then one other role that 3D can play, and this is something that was highlighted beautifully in Bolei's talk as well, was that 3D can serve as a mechanism for agents, like for more scalable learning by real to sim. So for example, collecting robot data is really hard, but we have a lot of examples of humans doing interesting things in environments. So here's an example of a human doing this rather complex locomotion or parkour motion, and we can use reconstruction to give a simulatable replica of this environment where we can train agents to learn policies in simulation. And we can do this at scale without having to manually teleoperate robots. Like, it's really difficult to, for instance, teleoperate a robot or a humanoid to do this sort of a parkour thing. It's much more scalable to make it see examples of humans doing this, make it practice in simulation through real to sim, and where 3D can play a crucial role in us being able to distill what we see in these videos to 3D representations where you could actually do this simulation for learning. Okay. So I motivated this talk by talking about the beta lesson, and then talked about these different roles for 3D for physical intelligence. But isn't this in contrast to the beta lesson? Why is it that I'm still advocating for using some 3D or some human knowledge despite what we learned from the beta lesson? And I would advocate that this is not really counter to the beta lesson. For example, Sutton really argued for not using methods that make our computational mechanism less general, and being wary of when we do this. And I would argue that these use cases are not sort of in contrast to that. So using 3D as a structural bottleneck can sometimes reduce generality, but it often would be a very practical solution where we can't scale data. And again, Chris's talk highlighted the data limitations. If we look at dexterous manipulation, this is even more severe. So when it's hard to scale data, these structural bottlenecks can be a very good sort of inductive bias that lets us build general systems without lots of general data. And I would argue that using it as a computational guidance does not really reduce generality. In fact, it increases the accuracy of this general computational mechanism like attention. And then efforts like Real2Sim, where we can use 3D representations to create more environments for learning, actually helps us scale even more effectively with computation. Okay. So yeah, with that, I'm happy to take any questions on this.
Thanks, Shubham. Let's take a couple of questions from the audience. So, what failure cases still exist in your pipeline, even with 3D representation integrated?
Yeah, so that's a great question. And I think the answer would depend a bit on each of these use cases. So for instance, if we use 3D as a structural bottleneck, then we're essentially saying that any computation we do has to go through this representation. And that is, often a point or could be a point of failure. For example, in the project that I was talking about, where we use this 3D tracking, 3D point tracks, it was a bit of failure that in some cases our model could not keep a track of how, or the reconstruction of 3D was not very precise, and then that implied the robot could not act in a very precise manner. But in some of the other ways of using 3D, for instance, if you're using 3D just as an attention modification in like a typical transformer, which is, let's say, the middle block, I'd say that is much more robust to these failures, because 3D is not really a bottleneck, it's just a guidance in this general mechanism.
So, do you think it's possible to do this kind of modeling in all scenarios? And also, Bolei mentioned that his robot has only maybe one camera. Is it going to be accurate to reconstruct this 3D environment?
Yeah, so I think even with one camera, so in fact, like maybe some of the teaser results that I'm showing here, all of these reconstructions that you're seeing are actually just with one camera. So we've made a remarkable amount of progress in being able to reconstruct even dynamic 3D scenes with just one camera. So on that front, I'm somewhat optimistic that even if you don't have 3-4 cameras, just casual videos are like, we are getting pretty good at extracting 3D information from the settings. And yeah, so I believe there's some reason for optimism there.
And we are also curious, what's the computational penalty associated with 3D?
So, let me think through this. So, okay, we've not, like, for all of these reconstruction or 3D reasoning results, you do require somewhat of a heavy GPU right now. So for instance, it's not something that is very easy to do on board with like a Jetson or a variant of that, but it's still pretty efficient. So for instance, these reconstructions that you're seeing here can happen maybe at 10 FPS rate. And again, this is without specific engineering efforts to improve this. So I wouldn't say it's a huge, the traditional 3D reconstruction that we used to do would be things like structure from motion. And that relied on extremely heavy optimization, which required lots of memory, lots of compute. The more recent methods are basically feed forward. You give them multiple images or you give them a streaming video, and they could give you a reconstruction of it. So we're getting closer and closer to basically online 3D reconstruction that is reasonably accurate. So I think for most of the recent systems, compute is not a huge issue.
Yeah, and I think I get the idea. You think 3D is essential, but do you think 3D should be on top of like large models and large scale data training, or 3D is important even with smaller models?
Yeah, so that's a great question. And I think maybe in this slide, like the structural bottleneck is what I would give you the most utility in smaller models, where you really are limited by data and can't train large models. But through this bottleneck of 3D, you can actually leverage large models for part of the problem, right? So for instance, this planning could use an existing video generative model, lift it to 3D. And so you've gotten augmented large data for free. But for settings where you do have lots and lots of data, I don't think 3D should be on top of the model. It should be kind of in the middle of the model, that your computation blocks, you can rethink to say, okay, I know that there's an underlying physical 3D world. How can my model better reflect those? How can the design of my model better reflect that? Okay. So we should not really be building these VLAs that, as Chris said wonderfully, are like chatbots with arms. We should really be designing them better to reflect the structure of the world that they are supposed to act in.
That sounds promising, and thank you for the presentation. And we will
Thanks
now
for having
move
me here.
Thank you for, to the next speaker. Our next speaker is Jiajun Wu, assistant professor of computer science at Stanford University by courtesy of psychology at Stanford University. Please welcome Professor Jiajun Wu.
Okay, yeah, thanks, Gaowen, for the introduction. Nice to see everyone here. I'm Jiajun from Stanford. Okay, so I'm going to talk about our work on physically grounded perception, reasoning, and manipulation. So, when we see a picture, when we understand and interact with the visual world, we realize the objects in the picture is not just pixels, right? There's underlying 3D structures that we would like to understand, including their geometries, materials, and their motions and other physical parameters like lightings and camera parameters. And the process of taking these, we call it like intrinsic parameters and produce the raw pixels is typically called like simulation or rendering, right? That's the problems in physical simulation and computer graphics. And for perception, we would like to invert the process. So we would like to ideally de-render and get these physical object properties from raw visual data. And nowadays, we have seen a lot of these efforts in people building foundation models. These foundation models are extremely powerful in, for example, producing raw pixels or images and videos, or generate from language or from a single image, or do visual language understanding. So our goal is being, okay, is that possible then for us to, is that possible for us to, if these models are so good at generating pixels and videos, is that possible for us to, they must have understand something about physics. So can we distill these physical knowledge that we care about, including object geometry and materials or physical properties from these pre-trained image and video generation models or visual language models? Right. So if you can generate a beautiful video of object moving, can we also understand the geometries of materials or physical properties of these objects, in order to solve our inverse problems in computer graphics by leveraging these pre-trained models? So to give you some examples, so we look at this relatively simpler problem of, is that possible for us to, given a single object, trying to do action condition dynamics predictions of the objects. So in this case, we're provided a static 3D scene, and our goal is to predict how the objects or the scene will respond to your actions. In this case, you have a flower, and the flower is going to respond to your actions. On the right, you can see our it's model output that you can apply different types of actions and forces and see how the flowers will respond. And you can see more results that we can apply different types of actions and see how the flower is responding to different actions. So to solve this problem, you really have to have a physical understanding of the objects that have, including objects like say geometries, but also their physical properties. And the challenge has been, okay, it's actually very difficult for us to model and represent physical object properties like stiffness, because if we want to learn them directly from data, there's actually no annotations, right? How much annotations you have for object physical properties like stiffness. And if you randomly assign these physical properties and say, okay, maybe I just give a guess of what is the stiffness or, like Young's modulus of the flower, it turns out the problem is very difficult and a random guess often doesn't work that well, right? So if you apply a random guess, you're going to see results like this, right? So apparently this doesn't look like a realistic flower, right? The problem is the flower, despite it looks simple, it is actually not just like, it doesn't have, I would say, a homogeneous stiffness value, right? Different parts of flower has different physical properties. So the problem with estimating physical properties is actually much more difficult. It's like higher dimensional. So in this work, which was done actually now a couple of years ago, led by Tianyuan, who is a PhD student at MIT, and Coben, who is my PhD student at Stanford, we thought about how can we distill physical object properties or all these physical intrinsics that we care about from pre-trained vision models. The way we did that is you take these 3D representations, you can render it into an image, send it to an image to video generation model, then you can get a reference video. The reference video is supposed to look actually very realistic because it's output of a video generation model, but it doesn't tell you anything about 3D or physical object properties. At the same time, you can have a physics field or material field that you're trying to estimate. You can let it go through a differentiable simulation and rendering pipeline, and you're going to get a rendered video. Rendered video is supposed to look very much based on your estimated physical properties. But as I said, because estimating physical properties is difficult, so based on your initial guess, which is probably incorrect, the rendered video is not going to look as realistic. But now you have a reference video. So what you can do is you can actually compare the two. You can compare the reference video and the rendered video, and even directly compute a pixel loss between the two, give you some signals about how your physical properties or estimations should be updated, because everything here through differentiable simulation and rendering is differentiable. So you can just use backpropagation to update your estimation of these physical object properties. And then you're going to iterate on this process and optimize and eventually get some physical properties that makes your simulated and rendered video look much more like those output from a video generation model. Right, so this extremely simple idea allows you to do pretty well in estimating a lot of these different physical properties for, in particular, soft bodies, because our simulators we use there is very good for soft bodies. So you can make it work estimating physical object properties, and then therefore for action condition simulation of the flowers, but also other types of objects like plants, hats, cables, and stuff like that. Okay. So later, we've extended the system to not only be able to estimate physical properties but of soft bodies, but also try to deal with other type of objects. For example, in this work led by also Gaowen and my new PhD student Yue, we try to estimate the geometries, but also the physics here, which is the velocity field of fluids and liquids and gas, which is these two-phase systems. And you can also model the interfacial dynamics between the liquid and the gas. You can see we're modeling the 3D geometries of the bubbles and how their velocities and how these, what are the surfaces, what are the interactions between the bubbles and the liquid. Okay, so in a different piece of work, we would like to try to integrate all these different models. We have models for soft bodies, we have models for fluids and gas. And is that possible for us to integrate them so that we can deal with the real world where it's really, it has very diverse physical phenomena. You have soft bodies, rigid bodies, and fluids and everything, interacting with each other. Right, so is that possible for us to have one unified paradigm that addresses all these problems? So in this problem of going from a static to dynamic interactions from a single image, our input now is the single image. We would like to turn it into 3D. And we would like to do action condition predictions to think about how these objects, which maybe in this case, a rigid body or a close to rigid body like a rubber duck, is going to interact with liquid, which is the sea, and you can apply different actions to it. In this case, it is gravity, right? So you want to integrate all these. You want to do a single image to a 3D reconstruction. You want to do action condition predictions. You want a system to work on not only a type of soft bodies, but also liquid and rigid bodies and everything. So here is video demonstrations of what we can achieve in that work. You can see that in this case, we're turning the image into 3D, and then we can apply different types of actions. For example, I can move around the stick. You can see the honey is going to drop down from the stick, and it's going to fall onto the cake. I can apply actions like, what happens if there's wind coming from a certain directions, and let's say the hat is going to move away, the hair is going to move accordingly. And again, everything here is you still maintain a 4D representation, so you're not just producing a video. You can also move the camera and see objects from different viewpoints. Okay, so to solve the problem here, we would like to integrate two things. One is traditional physical simulators. As I said, they can take physical properties and produce beautiful videos. But simulators themselves are insufficient because they have a lot of limitations. One limitation is there are a lot of things that we don't really know how to simulate. Right? Often the simulators are good for particular things like soft bodies or maybe others. And also, on top of that, they require perfect state estimation. right? As we just spent so much time talking about how much you can even get an estimation of physical object properties like stiffness, right? Just get one physical object properties take quite some effort. So it seems very difficult to get full physical states, including the complete object geometries and physical properties from limited observations like a single image. But the nice thing about a physical simulator or a physical model is it allows you to do action condition predictions for free, right? Because it's fundamentally causal. You can specify different types of actions. That's what it's designed for. At the same time, you have, as I said, you have these pre-trained video models as foundation models. It seems very great, and they have a few strengths, including they're very general, right? They should be able to deal with different types of objects. They have very strong visual priors that you can go from a single image and try to complete the missing regions. But their issue is they can't really take actions as input, right? Because there's no such data. You can take language or maybe some simple navigational commands as actions, but you can't really take very specific actions like, oh, what's going to happen if I put a finger or a dexterous hand, apply very complex actions into it, right? So these video models cannot take specific, very detailed actions as input. So our goal is that possible for us to integrate the two so that we can have some hybrid generative simulators, right? So you can not only use foundation models to distill physical properties, but you use these physical properties as additional conditions to allow you to better interface and control and interact with these pre-trained foundation models. So the way we did it is, let's say you take a single image and you want to build this kind of hybrid generative simulator. You first, have some 3D reconstruction pipeline that turns the image into 3D. And as I said, the problem is difficult. You can have missing regions, occlusions, and so the reconstruction is not going to be perfect. But even with the imperfect reconstruction, you can send it to a physical simulator, which is going to give you some rough estimations of, let's say, kind of intuitive physical understanding about how the scene is going to look like if you apply different types of actions. So here in this case, if you have wind coming from the bottom, you're going to see the smoke coming up and interact with the shoes. You're going to see a lot of these artifacts. The artifacts, it gives you some kind of intuitive physical predictions, but it's not perfect. You see all these artifacts, like it's not physically fully plausible because the shoe, it seems like the occupancy is not really modeled. You see some visual artifacts as well. But you can use these physical simulations as conditions for your video generation model, and allows you to have a much more realistic videos of, okay, how the smoke is interacting with the shoes, but this is just the video, right? It doesn't give you 3D, it doesn't give you physical properties. But finally, you can re-optimize these underlying physical representations to make it align with these generated videos, and sometimes even from multiple different views, right? So by doing this kind of re-optimization process, you actually get the best of both worlds. You make the video, or you make the 3D representations, their visual appearance look much more realistic because it now matches the video generation output. You still maintain this underlying 4D representations so that you can do action condition predictions, right? It looks a lot more physically plausible, but you can also move the camera. You can apply different types of actions to it. But this is a high level about what we did in this work called Wonderplay. And it does work on different types of physical objects. You can see you have rigid bodies like boats interacting with the river, soft bodies, granular objects like sand, rigid bodies interacting with each other, and rigid bodies like the shoe interacting with smoke. You can apply multiple actions in parallel. And because it's action condition predictions, you can even condition the same scene and apply different types of actions. You can see the different outcome. Right. So this was again led by my PhD student Gaowen and a new PhD student Zijiang. Once you can do all these things, action condition predictions, naturally you will say, is that possible for me to use it for robotics, right? So you can see now what happens if an action is a robot actuator, right? You can see the model is able to take robot actions as input and predict, how this underlying 3D scenes are going to change and behave differently, right? This is some follow-up work that we have been working on, as well as their direct applications to robotics. Okay, finally, let me maybe use a couple more minutes just to talk a little bit about our work on distilling or getting physical object intrinsics, not only from visual perception data, because there's not, your sensory modeling is very complex, and it doesn't have to be only getting from visual data, right? A very important aspect of it is it possible for us to build, let's say, for example, tactile sensing, right? So we have, all these tactile signals that allows us to also introduce and sense the same set of physical object properties like roughness, stiffness, geometries, and everything. So there has been a lot of work on building robust tactile sensors. We've been working on some of them as well. Some of these vision-based sensors have very high resolutions, but they're very difficult to design and customize, and they're not very durable. There are other, magnetic sensors, for example. They're much more cost-effective and durable, but it's actually complex and challenging to fit into different geometries. If you have different hands, different grippers, different sizes, it's hard to make to order. And they require, very data-driven estimations of contact size and forces. So our goal has been, we've been working with people from chemical engineering as a cross-disciplinary collaboration to design tactile sensors that has a lot of broad coverage and conformability, has cross-instances consistencies to be durable and repeatable, and also ideally give you interpretable signals for reward specifications. So what we did is this tactile sensors, most recently called DexSkin. So in DexSkin, it's like a soft skin that can make to order to accommodate different actuator sizes and shapes. We made it as a demonstration just for the fingers, but it can be made for hands and for other things as well. And it also is very cheap and durable. So in this DexSkin finger, it has a few components, including the rigid PCA core, a soft TPE sleeve, and an electronic skin. And within the electronic skin, it has multiple layers. Includes multiple layers of electrodes in horizontal rows of the finger, as well as a dielectric layer sandwiched in between. So this allows us to actually, simultaneously getting forces at multiple contact regions, and also allow us to conform it to different types of object actuator geometries, including in this case, the curved side of a finger. So the cost of making these sensors is only like $10, for example, for this finger. And you can put it on a gripper. You can also put it on fingers and multiple fingers, a hand and stuff like that, but we just showed it on a gripper. And here's a demonstration about the sensitivity of the sensor. You can see that we can have very slight forces, and you're going to see the robot is going to respond, the sensor is going to respond to the forces. And I think there's one more example that you just put, tiny objects, very lightweight, and the sensor is going to respond to the forces as well. And these kind of dedicated and also made-to-order sensors allows you to do very precise physically grounded manipulation. So not only just like perception, estimated physical properties, but also manipulation. Such as, is it possible for me to reorient the pen, let's say using obstacles, right? So you have to release the pen a little bit without letting it fall, but let it to be vertical. Even with external human perturbations, you can repeat a task, right? So this is actually very important, and you can only do that if you have the detailed tactile sensings at high resolutions. And without having the tactile sensings or without having the resolutions that you have, let's say if I just get the entire tactile sensor data and average it out, it is still not sufficient. You have to have the right sensing at the right particular point to really make it to be highly successful, right? You can see here it's a success rate with a full tactile sensing. It is almost always successful. Without having tactile sensings, it's not successful at all. And finally, here's a demonstration. And finally, we also show that this sensing can be adaptive to online learning in the sense that, once you try to pick up this blueberry, right, it requires your integration of visual data and also tactile sensing data as well, and to successfully pick up a blueberry. So we can compare a base imitation learn policy that doesn't require tactile sensing as well as our actuators and with DexSkin that does have tactile sensing but using a rigid policy to learn a gentle grasp. You can see that, after you train over time, the system learns to adapt and spend more time on focusing on force rewards to really improve the task success rate of blueberry picking. In particular, you can compare our residual policy that integrates this force feedback compared with the base policy that doesn't use the tactile feedback. You can see that base policy often squeeze and break the blueberries. And in comparison, our residual policy has a much higher success rate in picking up the blueberry without breaking it up. You can compare the blueberry output. You can see we have a much more higher success rate. Okay, so this was done by my PhD students, Stephen and Susanna. All right, so to summarize, I talked about contact-oriented manipulations via physics-based grounding. So of course, we want to use these very powerful learning methods and data-driven methods, pre-trained foundation models, vision language models. But at the same time, we want to think about, what is the role of these physical object properties? Do they still need to be modeled? If not, maybe they can serve as an interface for us to communicate and interact with these powerful foundation models, but also the same set of physical properties may support and service our other applications, such as manipulations, serve as a bridge to connect, let's say, data of multiple different modalities, from visual to tactile, right? So how can we really understand and model the role of physics, and how does that integrate the role of learning or these pre-trained foundation models? I think is still a fundamental questions. And the problem or the approach or philosophy we have been following has been to do perception and manipulation based on these physical object intrinsics, which are pretty universal because every object, is the universal physics, and every object is has object geometries, has physical properties. It is fundamentally causal. You can reason what's going to happen if I change the object geometry, if I change object physical properties, right? So this allows us to leverage this kind of hybrid approach, allow us to leverage these inaugural foundation data, inaugural data that has been pre-trained, that has been useful for pre-training these foundation models, but also allow us to leverage, let's say, data from physical simulation and synthetic data, and give us, in some sense, the interpretability of the structures and controllability of these foundation models more or less for free. Thank you.
Thanks, Jiajun, for the great talk. We have a lot of questions, but maybe we have time for only one short question. How does this modeling inform or makes robotic interaction with physical world better?
Yeah. So as I said, there are a lot of cases where you need to have, let's say, vision data, but also tactile sensings and physical property estimations, because you have a very good physical property estimation with the right sensing. Allows us to perform. If you just perform things that doesn't require dedicated manipulation, I just say pick up a cup, maybe that's okay. But in here, I think the strength of human manipulation is actually, it's not like it's the best of everything, but it's very flexible, it's very generalizable, it's pretty good at many, many different things, including operations that require dedicated manipulation, like picking up a blueberry. So to solving these problems well, you do have to have, in some sense, a more or less implicit understanding of physical properties, as well as very good sensings. So we're trying to build together, from hardware to software, to algorithms that estimate physical properties, that allows us to really have these solutions that allow us to solve these complex manipulation problems.
Thanks for the great presentation and discussion. Let's thank all the speakers again for the excellent presentation and discussion. We will take a break, and please come back for the next session at 10:22. Thank you.
Hi, everyone. Welcome to session 2 of the Cisco Research Embodied AI Summit. My name is Charles Fleming. I'm going to be your session chair for this session. We've got some great faculty members going to give some talks about their research and their sort of vision for embodied AI, the future of embodied AI. So our first speaker today is going to be Jason Corso. He's a professor of electrical engineering and computer science at University of Michigan. He's also the co-founder and CEO at Voxel 61, which is a computer vision startup that he's co-founded. So I'm just going to hand it off to Jason.
Thanks, Charles. Let me share my screen here, and then we can get going. Give me a thumbs up, Charles. All right, fantastic. Great to be here, folks. Yeah, my name is Jason Corso. I'm the Toyota Professor of AI here at Michigan in Robotics and EECS. This talk is about a journey over the last 20 years, in some sense, to building a softened boundary between human and computing through physically grounded upskilling, or physically grounded agentic upskilling. My collaborators are listed on the bottom of the slides here, and if you are interested in this type of work, just follow me on LinkedIn. I post daily about these types of problems and other things. So, as a kid, I was really enraptured by the notion of having a robotic or a computational partner that could help me through various problems, work alongside with me. And although, as a kid 40 years ago, that was quite a sci-fi reality, it may have been started by this commercial.
Will you be the one to witness the birth of the incredible Nintendo Entertainment System? The one to play with Rob, the extraordinary video robot, batteries not included. He helps you tackle even the toughest challenge.
I saw that commercial and I was like, whoa, there's a robot that's going to help me play Nintendo? Tackles the toughest challenges. And I was like totally overloaded by that possibility. If any of you are as old as I am, you know that Rob was a total failure and got taken off the shelves within a few weeks. But anyway, it was a fantastic idea for the future, I think, and it really laid some seeds in my world. And I've built a career in AI and like sort of physically grounded AI, primarily in computer vision, but across boundaries like vision and language. driven by that idea. So what exactly do I mean when I say physically grounded agentic upskilling? So let's look at something we're all familiar with, right? Like Nana's Kitchen here, where it's, like everyone's cooking, everyone needs to eat and so on. So like if we take this type of domain, and I love to cook, usually in the winter I cook soups. This is one example recipe that I was working with a couple years ago, I think, in a cold Michigan winter. And I love chowders. And so I saw the recipe in the recipe book and I was like, okay, let's get going. I can get the ingredients. I know what carrots are. I know what onions are. I know what the cream is and so on. And then step one, make a roux. All right, I'm an engineer. I don't have any formal training in cooking. I don't know what a roux is. I don't know if anyone here else also knows what a roux is. And I was like, oh my God, what do I actually do? So at the time, what I did really was go to YouTube and look for what is a roux? And I was able to work my way through it. It's like 15, 20 minutes. But okay, really, what is a roux? And like, is it possible that I could have had an agent in my kitchen that was participating with me, watching what was happening, to guide me through what a roux was in 3 minutes rather than in 20 minutes, and needing me to break and stop and go get my computer and so on, right? Like if we had these partners, could they actually help us through everyday life and make it better, right? So, and as many of you may know, cooking is actually bewitching to the field of AI and computer vision, right? Dozens of data sets, thousands of hours of video on YouTube. And I think it's really interesting because there are really interesting perceptual challenges, procedural challenges. Like you can follow the steps of a recipe and it can turn out awful. And you can follow the steps of a recipe and it can turn out great, right? Like if we had these AI partners, if we were able to be upskilled by either ambient AI or embodied AI, I think it might be a relatively interesting problem or solution. So I'll walk you through some work that we've been doing in this space. So here's a side view of the individual on the right, like a debug view, if you will, and we'll watch them perform a quick recipe. What's rendered on the screen back here is kind of like state estimation, of what the system thinks is happening. And this person's actually making what's called a mug cake. And you can just kind of see like computer vision AI is at the state of the art where in real time, this is all interactively output here. This video is sped up, obviously. We can do a real-time understanding of what's actually happening, and it's fairly high power, right? This is this is a DARPA-funded project that ended last year about perceptually enabled task guidance. But the kind of stuff that would be needed to build these physically grounded AI upskilling agents would need to be rendered here. For example, it would also need to understand whether or not a mistake is being made, right? Like here, I'll replay the video from the beginning, but he's actually pouring coffee beans to weigh them, which is not the step that the system thinks he's on, right? So like there's this misalignment, incongruence between what's happening in the real world and what should be happening in the procedure. And to build these types of agents, we really need to have that type of real-time monitoring and so on. So let me take you through a CVPR 26 paper that's coming out in Denver in a few weeks, actually, called Mistake Attribution with my group here at Michigan. So let's look at kind of like the state of the art in mistake understanding, right? So an attempt video was played here, right? And the task in this simple single task step was grab a chain whip. Let's play the video once more. Maybe you know what a chain whip is. Maybe you don't know what a chain whip is. All right. He grabbed something that was round at the top and had a long handle. That is not a chain whip. A chain whip has an open handle, a long handle, yes. It's partially open and there's a piece of bicycle chain on the end of the chain whip. So clearly that's not a chain whip, right? I didn't know what a chain whip was either before I began this work, but here we go. So the current state of the art lack diagnostic details. So it can tell, for example, that some mistake happened, and that it was like a modification in the procedure step or whatever, but it couldn't tell you spatially where it happened, temporally where it happened, or even semantically what was wrong with it, right? So we're creating a new, or in this paper, we define a new problem that we call mistake attribution, which takes the same input as the standard mistake detection work that we've seen in the computer vision literature in the last bit of time, and is able to attribute semantic mistakes. So is the predicate correct? Is the verb correct or wrong? Is the object correct or wrong, right? So in this case, grab, the verb, the action was right. but the object that was done was wrong, right? He grabbed a wrench, let's say, instead. Also has temporal attribution. So when did that happen? This is defined by the point of no return, for example. And then spatial attribution, right? What object and where was the object happening in the video that was wrong? Very quickly, if you kind of look at the mistake literature, there's no available data set for this. Most of the mistake-specific data sets are on the order of, say, 10 to the power 3 or 4 samples in them. That's just not enough to work with these days. Whereas you have Ego4D and Epic Kitchens that are 1 or 2 orders of magnitude greater, right? And so in order to actually do this, we need some other data set to do it with. And for us, we built this notion of a mistake engine. So we took available open data sets like Ego4D and Epic Kitchens and basically ran automatically processed SRL, basically pulling out the predicate and the object around these, what's the content of the video, and then just do mismatching and cross matches over there. So we can create mistakes just by manipulating the data that's out there. We didn't have to do any annotation manually, didn't have to record any new video manually. And that's what this mistake engine is able to give us. And it leads to a massive data set that has different types of mistakes that can happen at different times in the video, all automatically annotated. This led to what we call Epic Kitchens-M and Ego4D-M that have even more than the original ones, just because we could mismatch them, in fact. We also have annotation that's automatic for detection, semantics, temporal, and spatial from that work. And then to do recognition on this data set, we have this notion of a misformer that begins with a pre-trained VLM for feature extraction, nothing special here at all, and then is able to tack onto that custom transformer-based tailored attribution heads that are able to have the same common unified input in one framework and output semantic information, temporal attribution, and spatial attribution as well. Quickly, these new methods perform better than like off-the-shelf zero-shot things like ChatGPT, and also other sort of VLMs that talk to the notion of mistake attribution, even though they weren't fine-tuned on our data set, right? So ultimately, one would expect this to happen across semantics and temporal and spatial. But more interestingly, let's look at like some qualitative results, right? So like here are 2 videos. This is tie the stem. Instead of tying the stem, if you notice, they're clipping the stem on this side here, right? So it's the wrong verb again, but on the right object. Here on the right side, this is take a plate. And if you look at what they actually do, they take a mug out of it. And you can see that the system's able to automatically highlight when this is happening in both cases, and then where it's happening in both cases, right? So, and all in that one unified framework. Importantly, for interactive physically grounded agents, we have to actually anticipate when this mistake is going to be happening. So there's a lot more work to be done here, but I think this data set and initial end-to-end model is a really good contribution in that direction. Happy to reach out, happy to talk with anyone about the work. If not, I'll see you at the poster at CVPR. In the last few minutes here, though, let's look at how we're taking it out of the kitchen, out of canned data sets, and into reality for rural medicine in the US, or actually globally, but we have a project funded by ARPA-H. As you may know, there is a shortage of physicians and hospitals in rural America. In fact, from this graph in the top left here shows from 2012 to 2018, the distance a North Carolina citizen had to travel to get to their nearest hospital increased by 8-fold in the span of 6 years. It's horrendous. So I'm part of a project, the Vigil project on the PI and Vigil, which is funded by ARPA-H. And the whole goal is to build these vehicles, care delivery platforms, that will go and deliver rural healthcare and enable registered nurses and physicians assistants guided by these physically grounded agents to do specialist level care in the vehicle out in rural America just guided by the agent. So they're generally trained medical practitioners being upskilled on the fly. And we're part of this intelligent task guidance system. Before I jump ahead, I just want to note this is a large team, about 60 people across 10 universities, and really grateful to be a part of such an important project. So we have a physical environment that we built. Right now, this aluminum scaffolding is the inside of the, model to be the same size as the inside of one of those vehicles. We use depth cameras, real sense cameras, actual ultrasound, and so on. We have multiple IRBs, gathering sort of millions of images around the problem space. And cardiac care is one of the scenarios in which we're working. So we create a shared perceptual space in this physically grounded environment between the agent, the AI system, and the human on the right, and basically automatically do medical image processing and computer vision processing to deliver the type of guidance that we're able to upskill the practitioner on the fly. We do cardiac health, we do lower limb blood clot scanning as well. Like the image on the bottom right here is kind of like, this is a vein that they have to compress to check whether or not there's a clot or there's blood flow through it, for example. We do 3D sensing as well as part of this, all integrated into one system that's able to do this interactive, physically grounded agentic upskilling. We also create, in this shared perceptual space, we use not glasses because that creates a barrier between the generalist and the patient, but we use a projector interface to actually do that creation of this, like rendering to the agent what to do and to kind of augment how they can be guided. And we have a large swath of like.
Hi, Vigil, what's in this view?
This appears to be an apical 4-chamber A4C view with suboptimal visibility.
So the generals can kind of ask questions of the agent to help it walk them through the process of delivering that upskilling. So thanks for your attention. My viewpoint is to truly realize AI's upskilling and like human AI teaming potential. We really need to think about it as a collaborative agent that's working alongside humans rather than an autonomous replacement for those humans. Happy to take any questions. Thanks for your attention.
Hey, thanks, Jason, for your presentation. It was actually really interesting. So one question for you on the mistake recognition or identification part of your work. Does it primarily focus on like out of order or out of sequence task execution, or does it also recognize mistakes in outcomes? So, for example, I'm peeling a carrot and I accidentally drop it down the garbage disposal. That would be sort of an outcome mistake.
Yeah. Yeah, isn't it amazing how many ways things can go wrong, right? Like the number of ways in which we can make mistakes significantly outshines the number of ways in which we can do things properly. It does not look at outcomes, but it does look at more than just like interleaving of stages, right? Like the fair amount of the work in mistake recognition in instructional videos right now is like, wait, stop, you did C before A, or what have you. So it does try to get into you're doing task step A. Are you doing that task step properly? And if you're not, like, where are you doing it improperly? And what tool, what tool you're doing it improperly with, for example. So it's like a nuanced, attributed analysis of a specific execution of a task step, not the broader procedure in which you're doing that.
Okay. I guess there's a sort of follow-up question, and I'll sort of split it into two pieces. There's two sort of branches. So one of the things that you can imagine is that sometimes when you do things out of order, in fact, the outcome is not affected, right? Like there's certain things that I can do out of order, and it won't make a difference in the outcome. And simultaneously, like if hypothetically you were doing like mistake identification, there would be cases where like you would make a small mistake, and you wouldn't really maybe necessarily realize that's a mistake, like step N+1 or N+2. It might be several steps down the road. Do you think that things like world models where you could do counterfactual reasoning might sort of give you another tool for identifying cases where maybe you did something out of order but it doesn't affect the outcome in the end, or cases where you detect an error in execution, but that error is not going to actually bite you in the ass, as we say, until farther down in the execution chain? Do you think that there's any potential for that sort of thing?
Yeah, absolutely. So I mean, in this short 10 to 15 minute talk, I couldn't get into too many details. So under the hood in this thing, I'm not using the word agentic just because it's a marketing analogy, right? There is actually an AI agent, software agent that's running under the hood here. The AI agent has a representation of the procedure that's like, I would call it kind of like an explicit representation of the procedure and what should be happening step to step, and like what are the constraints between each of the steps and so on. And then that procedure representation is married with a world model that we've trained and adapted. Like in the healthcare case, as far as I know, we have the most general healthcare world model out there that we're working on, at least, and it's in review right now. But anyway, and those two things together work to even do things like tool calling, right? Like when the user says like, "Hey Vigil, I'm not really sure if I should use a knife or a fork for this or whatever," right? Like that actually executes like a tool calling agent or agentic subprocess that decides, is this like a medical VQA question, or is this like a general world knowledge VQA question? Like all that happens. And so it is responsible to continuously decide, should I interact with the human in a way to pause what they're doing and reflect on, like, stop now, are you sure you should be doing this, or you should be doing something else, to anticipate things like you are suggesting, right? And the only way we could do that automatically, the only generalizable way we can do that automatically, is with a contemporary world model.
Interesting. Yeah, that's interesting to know. So it feels like there's a convergence here towards these types of things. So there's one more question from the audience, and that's, what's the biggest bottleneck, lack of data, model hallucinations, et cetera, in this work?
Yeah, I mean, I think there are actually, we just finished a site visit yesterday for the healthcare project, so I'll probably give you more of a technical answer than a researchy answer. The biggest bottleneck is the quality of USB-C cables and how well they can get connected and not fray in the middle of a demo. But anyway, so it is, we like to think that the world of YouTube and all the world's textual data that was farmed from the web is actually a good representative reality of what actually happens in like egocentric and localized challenges. Unfortunately, it's not, right? Like we're using many both off the shelf and fine-tuned perceptual models like VLM type models and LLM models and even like 3D pose estimation models. Vision is not as robust as we like to think it is when it's used in localized real world settings that has to have interactive feedback. Do we need more data for that? Yes. Can we go and argue to the funders of the project that we need to go invest 3 years to get that data? Absolutely not. Right. So there's this weird duality in like where the real tension is and what we researchers think we're making real progress in versus how that progress is actually mapped into interactive settings. Interactive vision is very different than download a CVPR paper, wait a week to get the results from your benchmark cluster. And I think we need to get our act together as a field to do things with more interactively minded.
Okay, great. Yeah, that's great. Thanks for your talk. I appreciate your time. Very, very interesting work. I realize I need to go and read some of your papers.
Awesome. Thanks.
So our next speaker is going to be Lirong Xiang. She's assistant professor at Cornell. She leads the automation and robotics lab. Her work mostly focuses on robotics applications in agriculture, computer vision, and machine learning. She's also a collaborator of mine, so I'm happy to hear her talk today. So take it away, Lirong.
Thank you, Charles, for the great introduction. And I will go ahead and share my screen. Does it work?
Yes.
Okay, good. Thanks. Well, very happy to be here to share my 2 cents about embodied AI. So as Charles has mentioned, my experience mainly comes from agriculture, but this is such a representative physical world. Well, it consistently challenges our assumptions about robotics and AI. And I will also share a couple of emerging directions that I can think of in this area. So I wanted to start with some of the representative challenges in this area and also the questions that I'm very interested in. What happens when we bring robots, when robots leave the lab and operate in open world environments. For example, in the left image, a robot stuck in the muddy soil. So agriculture really happens to be a very representative test case for embodied AI systems because it combines all different kinds of challenges, such as very unstructured environments with muddy soil, uneven terrain, changing lighting conditions, wind, narrow working space, like what I've shown in the right image. And in many cases, embodied AI system can fail in those scenarios. So along with this unstructured environments, there are also challenges to the perception system because of our dynamic sensing environments. For example, like the uneven lighting, non-uniform illumination, and objects are partially occluded, and the environment introduces noise that looks quite similar to the anomaly we are looking for. So you see examples where physical damage and background clutter and foreground occlusions, they all create similar signals to confuse the perception systems. And another representative challenge in this area is occlusion. Even though when we have the right cameras and the sensors, sometimes the important information is often hidden or partially occluded. For example, in tomato disease scouting, the symptoms, they might start inside the canopy, as the picture is showing here. There are lesions on the stems, leaves, fruits that may be covered by foliage. So from a single viewpoint, the robot may only see the outer leaves, while the real target is partially occluded or completely occluded. And this becomes an important question, like should the robot system move closer, changing viewpoint, push leaves aside, or use another sensing modality? So I think one of the future directions is not only to build a better perception system, but also need interactive perception, a system that actively interact with these complicated scenarios and actively decide how and where to see. And this is also where those foundation models like VOA, large language models become exciting. And since they can help with connect high-level goals and visual observations and physical actions. So I've been talking about some representative challenges, including, unstructured environments, dynamic sensing environments, conditions, and occlusions. But all those challenges bring a lot of opportunities for new capabilities of embodied AI systems. So I'm going to share a couple of emerging directions I can think of with our example research projects. So in this case, the first emerging direction, moving from passive vision to active perception. So where the robot system can decide how to interact with the scenario and how to collect information, where to look at, and what viewpoint may reduce uncertainty. And this becomes very important, especially in narrow or constrained occluded spaces. An example here is in this scenario, many tomato fruits and the disease symptoms, they are hidden inside the canopy, and standard external camera may miss those important symptoms. So we have developed this plant endoscope that can go inside the canopy, rotate around, take multimodal sensing data, and to detect those anomalies. And so I think one direction is that those embodied systems will have a small multimodal sensing that can move into those constrained spaces to gather information from viewpoints that are normally inaccessible. And this video showing how it looks like when such system combined with mobile platform and manipulation. So instead of assuming all useful information can be captured from one fixed viewpoint, this embodied system can first navigate through the row crops and identify regions of interest, and then move its sensor or arm closer to the target area, like a target fruit. So in this kind of setting, perception becomes more interactive. The robot will begin with a broader view and then reason about where uncertainty is high, where symptoms may be hidden, and where what action can generate better observation. And the second emergent direction I want to share is moving from those static systems to more agile system. It is not enough for a system to have strong perception capabilities, but also need the physical flexibility to move, adapt, and recover when the environment doesn't match the plan. So in this example, in agricultural scenarios, for example, there are some relatively structured scenarios. For example, a cornfield with row crops. And in another case, the scenarios, the plant canopies are dense, narrow, irregular. For example, a cucumber field is kind of a sea of plant canopy. So this same contrast appears in many other domains, such as warehouses, disaster sites, forests, construction sites, and other human-centered environments. And the point I want to convey is we really need agile system that can be flexible in morphology. For example, the robot I'm showing here, we developed a legged robot that can change its shape and morphology to adapt to different terrain. And it can also use one of its legs as a manipulator to do dexterous operation. For example, dropping a micro volume herbicides on the weeds. So the key question is how such embodied AI system can become more adaptive to physical world. And the example project we have been working on is this dexterous legged robot. Well, it can enable the system how it senses and where it can go and how it interact robustly, recover from uncertainty. For example, navigate in this cluttered crop field. So this is a video showing some of the capabilities. And one example is the multimodal sensing. Besides the visual system that provides the semantic information of the field, it also has tactile sensing on the foot to tell what type of object it is. So, for example, when a vision is uncertain, especially beneath the robot legs, by touching the surface based on the tactile sensors, it can distinguish whether it's contacting a stem, leaf, fruits, soil, or background structure. And based on that information, the robot will adapt its gait and update its foothold and chose a safer shape, morphology to pass through the clutter. And another important feature you have seen from the video is this adaptive morphology. When there's an obstacle, instead of going around, the robot will change its shape, increase its clearance to step over the obstacle. I will skip a little bit. So this is an example where the robot will increase the clearance and step over the obstacle, and this is where the robot will update its foothold to avoid damaging the leaves and fruits. So with that, the third emergent direction I want to share is the multi-agent intelligence. So moving from a single robot system where to multi-robot to a distributed system where different agents will collaborate. So in many real-world environments, and especially in agriculture, one robot may not be the best solution for everything. Some agents may have better at sensing, some at planning. For example, a drone system in this case can scan a field in a very fast manner and provide a global view and use that planning information for other distributed robots. And a ground robot may inspect plants at a lower section or even inside the plant canopy. And a dexterous robot, like a legged robot, can perform precision or even ultra precision action, such as dropping the micro volume herbicides on the weeds. So what becomes interesting is how those agents can collaborate, communicate with each other, coordinate with each other. So we've been leveraging large foundation models and language models to provide the interface for high-level reasoning and to understand the human instructions and break them into subtasks and assigning rules to sub-agents like those specific individual robots. So this is an example project we have been working on using multi-agent robots for precision crop management. And one of the key components is this interactive user interface. So it takes the natural language as the inputs, and behind this interface, it connects directly to the LLM agent, which continues to reason over a structured representation of the field state. And then behind this, we have a heterogeneous robotic team where we have an aerial robot that provides the top view of the field for global sensing, and a ground robot for local inspection, and a leg robot for precise localized actions. And each robot is abstracted as a tool so the agent can call. And we also build this digital twin system to simulate everything and see the outcomes before we really apply the real actions in the real world. So this future direction is, rather than smarter individual robots, well, the embodied AI will be a distributed system. Well, the perception, planning, and action they will share across multi-agent. And this is a very specific application to show how those multi-agent the system work together. In this case, we want to address the weed problems in crop fields. And at first, the robot will scan the whole field with a very fast manner, probably in 5-10 minutes. And the system will detect the weeds, including different weed species, identify the weed locations, and send that location to localized robots, for example, the spider robot, leggy robot, to do the precision spray on the weeds. And at the end, the whole system will recheck to double check all the weeds are removed in the field, and also generate an updated map for the growers or stakeholders. And we've also
Speak Plan
tested
Harvest, an ELM agent for general planning in agriculture via transfer learning. The system coordinates a heterogeneous team of 3 specialized robots. The aerial bot, implemented as a gantry robot or a drone, performs initial field surveys from above, providing critical top-down views for mapping. The Husky bot, a ground rover, is deployed for detailed, ground-level inspection, capturing close-up imagery of individual plants. And the Spiderbot, a hexapod robot, serves as the intervention unit capable of performing precise, targeted actions. Here, we demonstrate a real-world task: to find and treat all diseased plants in the field. The process begins with a farmer issuing a high-level command in natural language through an intuitive user interface. The ELM agent interprets this command. Its first step is to plan and execute a field-wide scan, using the benchbot to locate all plants. With the plant locations now mapped, the agent's plan proceeds to the next phase, detailed inspection. It dispatches the Husky bot to systematically capture the side view images required for disease analysis. Once the ground-level images are collected, the agent can begin the perception and diagnosis stage. The agent sequentially invokes its perception tools to analyze the images. First, detecting the presence of disease. Then identifying the specific disease type, followed by its growth stage. And finally, assessing its severity. With a complete diagnosis, the agent formulates the final action plan: precision treatment. It commands the Spiderbot to navigate to the affected plants and apply fungicide directly to the targeted areas. After all these processes, the mission is completed. The agent autonomously recognizes the end of the task and stops.
So at the end, I want to share this video to connect all those emergent directions I've shared together. And this is one of the most labor-intensive tasks in agriculture, pruning. People do that a couple of times each week, and we really want to automate the process to save the labor cost. So assuming we want to have a robot to automate the process, so as you can tell from the video, in this case, the robot is not simply cutting a branch. It will need to operate in a dense, deformable, and partially observable environment. and avoid damaging those fruits, stems, and leaves. So here comes a very important embodied AI question. How do we develop a system that can continuously do a continuous perception, learning, and execution loop? So there are many challenges there, also bring us a lot of opportunities. For example, we can use a visual language model system to not only recognize where it is feasible, but also decide how to move, where to look, and guide the robot to reduce uncertainty. And the second point, like I mentioned, the agile system, we will need a small, agile, dexterous system to interact with these delicate and deformable structures. And last but not least is the distributed idea I've shared to scale such a robotic system beyond one plant or one greenhouse. We will need a system that can learn from different agents like human demonstrations, multimodal sensing, and also coordinate across different agents and cases, and can be scalable across different greenhouses and scenarios. So thank you so much for your attention. And here I want to acknowledge students, collaborators, and all the funding agencies who made those projects possible.
Thanks, Lirong. So I'm having a little bit of problem, so I'm on my phone. I apologize.
Oh, really?
Thanks for the
Sorry about that.
presentation. Yeah, no, I think it's Xfinity, not you. So I think that agricultural robotics to me is one of the most transformative opportunities with respect to like sort of human prosperity. That there exists for embodied AI. I mean, if you think about like, people think about like, I'm going to lose my job to these robots, but if you think about like the mechanization of agriculture, it's really resulted in really just a lot more food, a lot cheaper food. If you look at like, wheat and corn and other things that can be mechanized. So embodied to me has like that opportunity to come in and do that for all the other crops that we couldn't mechanize in the past, like tomatoes and cucumbers and watermelons.
Yeah.
So I see it just as an opportunity to improve the situation of like people, just the average person, cheaper food, cheaper vegetables. So given that though, what do you think, these sorts of robots, what are the sort of the capabilities that they have that people don't have, or that it's not really financially feasible for people to do? You can't just pay someone to go out and do just anything. It doesn't make any sense. What do you think are the opportunities here for these types of systems?
Yeah, thank you so much for the great point. I think the robotic system in agriculture are not only providing cheaper food, but also mitigate the challenges like labor shortage and labor safety, etc. And regarding some of the new capabilities that currently human being cannot do, for example, tracking the crop growth. So with a robot, like the collaboration, we have been working on the visual memory framework. It can keep the historical data, how the plants grow from flower, fruits, and how the pollination efficiency looks like, and how that affect the fruit quality, shape, size, and other flavor, etc. So the robotic system can keep those and also analyze those historical data to do a more intelligent management of the crop to produce better fruit for human being.
Okay, yeah, no, I think that's great. I think actually that answers another question from the audience, which was how much does it leverage past history from the environment, which, like you said, is something that you're working on currently.
Yeah.
So I think we're actually out of time, so I need to jump to the next speaker. So I'm gonna thank you for your time, thank you for your presentation, and I have a lot of hopes for this research direction. So
sure, thank you.
Thank you. All right, so our next speaker is going to be Achuta Kadambi. He's an associate professor of electrical and engineering computer science at UCLA, a school I'm quite fond of, where he leads the visual machines group. He's also co-founded 2 companies, Akasha Imaging and Value Robotics, both of which have since been acquired. Thank you, and then we're looking forward to hearing your presentation, Achuta.
Thank you so much. Let me share my screen here. Okay, just want to make sure that You can see the screen?
Yeah, but it's not in, yeah, there we go. Now it's in presenter mode. Perfect.
Okay, excellent. So let me just set a stopwatch. All right. So the title of this talk is Where Are World Models Heading? It's a word that we heard earlier in the talk. And before I even jump in, let me just demystify some buzzwords because we see them all in the news. VLM, VLA, world model. And so these are the three common words that we see, all very similar. The VLM is broadly vision language model. That's perhaps what we're most familiar with. VLA is just like a VLM, but you add an action. Actions are often, but not always, embodied. And then a world model, the real key is that you have these counterfactual future state predictions that you can do. Whichever word you choose, the common theme here is spatial intelligence. And so I should really probably have retitled the talk, Where is Spatial Intelligence Heading? Now, these are the three directions that I'm particularly interested in. It's not exhaustive. I'm going to talk about the first two in some detail, and I'm going to show you at the end the slide again to put it in context. So what I'm going to talk about is mostly small data approaches. So stuff that a university or a small industry team can do. You don't need to raise billions of dollars in financing to collect internet scale data. And a lot of what I'll discuss deals with then lifting stuff that works in 2D, like widely available 2D foundation models, and bringing them to 3D or 4D scene understanding. So let's talk a little bit about what I mean. When you have a 3D scene, we've seen seminal works in the past half decade that essentially build up the 3D scene and represent its geometry and appearance. So very famous work is NERF, where you can have different views of the scene and you get geometry and appearance. More recently, you have another very famous work on Gaussian splatting, where you can take a scene and represent it by these Gaussian kernels, and the composition of these Gaussians will allow you to encode novel viewpoints and essentially compress the scene into Gaussian functions. So while this is super useful, one of the open questions is what's happening with perception, right? So perception deals with semantics, which is a layer on top of the geometry and appearance. So if we had a regular 3D scene and we didn't just want perfect geometry and appearance, but we wanted to know in 3D that this is a table, that this is a chair, this is a car, so on and so forth, we'd have to put semantics on top of 3D. The problem with this is that we don't have essentially large internet scale data to train 3D or 4D foundation models. What we do have is we have these 2D foundation models. And so one of the papers that we had was how we can supercharge this to effectively take 2D foundation models and then lift them up to 3D. And so here's what I mean. You have the Gaussian splatting in 2023, which I mentioned, which gives you a 3D reconstruction of the scene on the right-hand side of a city street in Europe. Now, if you look at this, you have the geometry and the appearance. We want to add semantics to that. And so what we're going to do is we're going to create a feature field by using a 2D foundation model to kind of upsample that into a feature field on the radiance field. So if you can do that properly, then what you can do is you can do semantic segmentation, you can do language guided editing, you can do segment anything. Again, even though I'm showing images, these are really happening in the 3D space, in the radiance field space. So if I were to rotate the viewpoint and move around the scene, I would be able to see all the objects segmented. The way we achieve this is we use teacher-students idea. So essentially think of the 2D foundation models. Let's assume that they're pretty decent, pretty good. They have internet scale data to train them. And so you can use them as your 2D foundation model as your teacher, and then create like a feature embedding and then compare your loss for your student, which will be a 3D spatial intelligence model. So this is like a more complete architecture. Basically the inputs and outputs of what we're developing, which is that 3D spatial intelligence should match the 2D foundation model. So in a nutshell, you take your 3D scene, every 2D projection of that 3D scene, when you put that 2D projection into a 2D foundation model, the image and latent space should be corresponding to the teacher. Okay, so it's basically splitting up the 3D problem into a bunch of 2D consistency checks with the 2D foundation model. All right, so we did this for static scenes, and we were able to have this level of 3D scene understanding, which then you can use downstream in a lot of embodied tasks. But an important question is, what about adding the time dimension? A scene is not just a static scene with a few different viewpoints. You have things moving around in time. And so we followed that paper up in the next year's CVPR conference by lifting, again, the 2D model to 4D. So essentially, you have a video now of let's say this dog on a ledge, and what you're going to create is not just a 4D radiance field where you can have the geometry and appearance in 4D, but you're going to have like this latent space, this feature field in 4D, and then you can put AI on top of that. So this is a little bit of the architecture. It's a little bit of a mouthful, but it's very similar. It's lifting what we did in 3D, but lifting. The problem now is that the projections become a little bit more complicated in how we get those 2D projections from a 3D model. Here's a few results. Here's an input video that we have. And what we can do is we can obtain radiance field representation in time, as well as in the rainbow image on the right, you have this feature field. And so you have this radiance field, you have the feature field, it's dynamic, the features are changing. And once you have a feature field, you can basically put different sort of task-specific heads on top of it for neural nets. And these heads can basically output different things that you want. So one of them is like segmentation. So if I look at the localization problem, you want to segment that dog. You can give the prompt in one view at one step, and it's going to propagate that prompt as the video continues. All right. So you're only segmenting the dog once with the model, but it enforces that consistency throughout the video. A second thing you can do is recognition, semantic scene understanding. So you have 2D clip, and you can then lift that to the radiance field. And so now you can change, let's say, edit the dog's color to look like Clifford the dog. You could delete the dog, and you see it propagates again through the 4D scene, which is the video and different viewpoints. And of course, you can extract the dog. So in a nutshell, you're again able to use your image editing, but now instead of 2D image editing, you're doing it in 4D. Finally, another application is visual question understanding. Which direction is the dog moving? It's something I'll touch on a little bit more. The dog is moving to the left. How many window shutters are there? There are 4 window shutters. So in this particular application, you're doing a global VQA on the scene. So it's not viewpoint by viewpoint. You're using the entire 4D field as your latent space. And then on top of that, you're able to answer these higher level questions that are more rich because they take into account the 4D scene context. Okay, so going back to the talk motivation, where is spatial intelligence heading? One of the problems that I think was touched on in a couple of the other talks is, do VLMs really understand the spatial relationships in the 4D world? Spatial relationships being one of the foundations of physical AI. And so we had a paper in ICCV that's called VLM 4D, which is effectively a benchmarking paper. And let me just give you an example to illustrate. So look at this video. So the question is, from the camera perspective, what direction are the cyclists moving? And if you look at it as a human, and you look at it from your orientation, you would say that the cyclists are moving left because we have that convention. Now, if you put this into an AI model like GPT-4o would give you this answer, which is obviously not correct. Put it through Gemini, and you actually get back a very similar answer, which is incorrect. And so even though the cyclist is obviously moving to the left as a human, AI does not know left from right when it comes to reasoning on top of images. This is exacerbated if you look at, out of plane motion. So in this particular case, from the camera's perspective, you prompt an AI model to tell you what direction the car is moving. Again, you and I know that it's moving to the right, but a VLM would say that it's moving to the left. Now, if you build a foundation of like VLAs and do actions based on this, this understanding, you would end up colliding in the real world. So when we saw this problem being kind of one-off, when we would just drag this into like our favorite AI model and we saw that it was getting left and right wrong, we decided, okay, let's scale this up and let's make a benchmark for this. So we took real videos, we took synthetic videos, we took from first-person viewpoint, we took from exocentric viewpoint, meaning outside, egocentric, exocentric, so on and so forth, and then had comparisons to humans. There are approximately 1,000 videos with approximately 2,000 questions. It's not just left and right. You have clockwise, counterclockwise. You have relative positions where you ground it to like other objects in the scene. And then you ask things like, you know, for example, if you were to think about things from one view or another, how would that look? So here's an example. Here's a jet ski. You can see that if I click the video, it appears to be rotating, right? And this is an exocentric rotational motion, meaning that you're looking at the object that's moving from outside the object, exo. And so, you know, as a human, we would be able to understand and get the answer to this being clockwise, right? Here's another example. This one is a little bit more involved, right? We have to kind of use our brains as humans on this one. So the cat, right? Is the cat turning to the left or right from its own perspective? Okay. And so you're testing whether the VLM has this spatiotemporal reasoning from different perspectives, right? A VLM for robotics and embodied systems needs to be able to understand embodiment in other agents to understand relative positioning. Here's another example. Which direction does the person turn to pick up the branch? And it's egocentric. It's from first-person view. And you're looking at a little bit of rotational motion question here. Okay. We have these questions online on the paper website. But here's a confounding example we also added. So which direction did the dog move? Well, if you look here, there's no dog. All right. So the VLM should also understand a little of these trick questions that test their critical thinking. The bottom line is, how accurate are, you know, current models, state-of-the-art models? Well, they're accurate on these questions about, you know, 60% of the time or so, right? Things have improved. Quarter on quarter, the model has improved. But if you compare to a user study in a human, outside of a human being fatigued, the human is accurate 99% of the time, okay? And it's true that VLMs, if you look at the second row as random selection, VLMs are better than like randomly choosing the answer. They're about, you know, twice or 3 times as good as random, but that's not good enough to have like physical agents that are, you know, doing actuations in the world. And, you know, building world models on top of this and reasoning about counterfactual is going to be very hard if you don't know left from right. So why don't VLMs understand left and right? Well, the answer has to do with latent space. Think about latent space like a transformer embedding textual concepts like left and right. If I embed left and right in a VLM, it's going to embed in a similar space because they're semantically directions. So left and right will embed in a similar space, just like king and queen will embed in a similar space. The problem is that left and right in the physical world are opposites. If I'm doing Gen AI and writing a novel, like it doesn't matter if Harry Potter turned left at the Chamber of Secrets or if Harry Potter turned right to get into the Chamber of Secrets. But in the physical AI space, you do need to know this answer. So you can do various things to solve this problem. You can try chain of thought reasoning to improve it. You could do studies on different videos with richer captions. But you know, one of the things you can do with this data set is you can supervised fine tune it on data sets like VLM4D. So you can see that the original model is like maybe 40% accurate. The fine-tuned model will be 60% accurate. So having good data is important, and then fine-tuning on it is useful. Maybe this will scale up. We did this in an academic lab with 2,000 videos. Maybe if you did this at scale, you'd be more accurate. I don't think you'd get to the 99% human accuracy. Another approach is to use some of those 4D ideas where you basically have the AI do analysis by synthesis, right? Effectively, it reconstructs the 4D scene with the 4D features and then does the querying on top of that. So it brings some of the ideas in the talk I mentioned earlier. So regardless of what solution you actually choose, this lifting works better. But regardless of what solution you actually choose, the point is that spatial intelligence has a ways to go. As I open it up for Q&A, I want to list 3 kind of problems, pain points with spatial AI, and then how that impacts tomorrow. So today we don't have an internet scale data for 3D. And while it is true that some companies, which I won't name, are well capitalized to try and get this internet of 3D data, I think that tomorrow we will see more small data approaches like lifting play a key role. I don't think just scaling the data is going to get you to human level accuracy there. That's just my personal view. Today you have these behind, near, graspable, these kind of affordances. They're relational and they're embodiment dependent. And so tomorrow we're going to see more models and grounding spatial intelligence, kind of follow-up work to what I mentioned. A direction that interests me a lot, and it's a little bit speculative, I don't know how we would exactly do it, but embodiment lacks supervision from images. Like, for example, if I'm in a scene and I see that this chair is like rickety and wobbly, and if I sit on it, it might collapse, it's hard to get that information just from the image alone. Right? You don't know the stiffness of the chair just from an image. And so I think tomorrow there's going to be more work in what I call toe in the water approaches, where you dip your toe in the pool to kind of measure the temperature, where you send some sort of cheap action to the scene with a VLA, like, for example, wobble the chair yourself as a robot, and then see if that gives you a video signal, which then could give you better supervision for embodiment. So that's going to be pretty cool, like these little test actions that we're going to have in the scene. With that, let me cede my time here and open it up for QA.
Okay, we got a few questions. Actually, I think we got a little time. The first one is, I know that Gemini, Google has this Gemini embodied reasoning model. Have you tried that to see if it's any better? I'm just kind of curious. Have they done a better job with that since it's supposed to be targeted for this type of work?
Yeah, I don't have the numbers on hand, but we did try newer models from the paper from Gemini, and they were better than what's in the table. They weren't at 99%. They were getting up to it went from like 60 to 70%. But definitely we'll look into that and maybe check in on what those results would be.
Yeah, just curious because it's explicitly trained for this type of thing. But so some other questions from the audience. Do you think that we can fix this by explicitly RL gemming with such data? Because the gap could be because they're not explicitly trained to distinguish left and right, I think in this case. Yeah.
Yeah, I think that's one solution. I think RL, basically a closed loop RL approach to this could help quite a bit. Getting to 99% is a tough ask, right? Like humans are basically perfect on this left and right to the point of fatigue, right? And so I'd be curious if kind of for every action, like an AI could do it. It's kind of like how AI can multiply and add, right? Like it can't really add numbers. You have to call a calculator. I'm curious if we would end up with some sort of explicit coordinate system or optical flow approach that becomes more useful later on. But yeah, I think it's a good direction to try. And there's some works on that as well that I think are coming up at CVPR this year.
Okay, so let's see. The last question is, how does this tie in with world models specifically? Maybe you touched on this a bit, but it seems like spatial intelligence should be across all 3 types of models: VLM, VLAs, and world models.
Correct. So kind of I adapted the talk a little bit. World model is more about the future state prediction. I think if the foundation of spatial intelligence is not there, all those three models, VLA, VLM, and world model, are going to have some challenges. So yeah, that question is exactly right.
Okay, well, thanks for your presentation. I appreciate your time. And that's the end of session 2, and I'm gonna hand it off to my colleague Jiant. So take it away, Jiant.
Thank you.
Yeah. Hi, everyone. It's been wonderful 2 sessions so far, and I'm happy to kick off session 3. It's my pleasure today to introduce our next speaker, Dr. Upinder Kaur. Dr. Kaur is an assistant professor in the Department of Agricultural and Biological Engineering at Purdue University. She earned her PhD from Purdue, where she conducted research in collaborative robotics lab under the guidance of Professor Richard Bolles. Her work reimagines cyber physical systems by utilizing robots as mobile, dexterous edge devices to create more responsive interfaces between the physical and cyber worlds. Notably, her research focuses on deploying resource-aware robots to solve complex challenges in austere environments, including her pioneering work in precision animal agriculture, where she's even deployed robots in cows to improve welfare and productivity. Here's Dr. Upinder Kaur. Please take it away.
Thank you, Jen. Thank you for the introduction. Hi, everyone. I'm Upinder. I'm an assistant professor here at Purdue. And today I want to talk about more on the perception side of robotics and embodied AI. I hope everybody can see my screen.
Yes, we can see it. Thank you.
So the research vision of my lab is to build autonomous systems wherein we take a systems approach to deliver resource-aware and dynamically adaptive systems that can work in the unstructured world. So robotic perception today, essentially, is generally comprises of vision, which is standard RGB cameras and depth cameras. LiDARs are very common in autonomous robotics today. And manipulation-based robots also use tactile sensing for contact sensing. While these are very capable in the structured, planned areas like the factory floors and urban environments that you see them now, my work is more on the unstructured side of this equation, right? So the unstructured world of, for example, construction zones and farms are still an open challenge to the standard perception stacks. These environments are uncertain and dynamic with fast changes causing calibration issues for lighting, depth, and flow, often causing downstream planning and motion to fail. This is particularly critical for examples in cases of mowing around the highway, as you can see here, where lives are lost annually due to the lack of robust automation systems that can operate reliably in such unstructured environments of a sloped, muddy field with fast vehicles going on both sides of you. Similarly, for construction environments where things are going to change every hour. So traditional SLAM and other algorithms will struggle if you don't have a way of capturing that change fast enough. This is a critical concern for a lot of agencies like Indiana Department of Transportation, DARPA, USDA, and so on. So the question then becomes, how do we build perception that remains reliable when the world is unstructured, dynamic, and only partially observable? To bring this into focus, let's imagine a scenario where you're going through a tunnel, right? For a few seconds, it takes your eyes to recalibrate to the change in the lighting level. This is as there is a sharp lighting change. Even RGB cameras, which are standardly used in autonomous systems, also take a few seconds to refocus. But for an embodied AI or autonomous system, it is important to maintain perception fidelity, especially at high speeds for safety. Similarly, low light conditions can also cause perception issues as you're not able to perceive the full field of view with enough confidence. In my research, we augment this by using event cameras. Event cameras are dynamic systems or dynamic vision cameras that can sample as fast as a few nanoseconds. Unlike RGB cameras, they do not have a fixed sampling rate and are triggered wherever there is a change in the environment. So as soon as something is moving, that's what they're going to capture. They do not care about the static objects in your field of vision. And this capture can be as fast as 10 nanoseconds. They do not also care about the intensity of the light. So they do not need that recalibration to happen as you go from a highly lit, controlled environment to a much more unstructured environment. This is a key ability for perception systems to incorporate into existing stacks to work in challenging and dynamic environments, particularly as embodied AI, where there is a much higher risk and need for safety. But event cameras generate sparse streams, as you can see here. This is a stream of just an object moving, and most of the stream looks empty, right? Because it's only going to capture the object and the pixels where there is a lighting change being picked up. While this is beneficial for edge computing, as you're only dealing with a fraction of the data than a regular RGB image, so you can work on much lower resource edge devices. This leads to integration issues if you want to directly use this with downstream deep networks, as such sparse data will cause them to diverge. So AI models will bias towards the null here and will not converge on the raw event streams. Current methods to overcome this lead to temporal binning, where they try to condense this event stream into one image or a slice. But that actually slows down the speed of perception, therefore nullifying the main use case for event cameras. In our work, we use adaptive frequency-based patching to create a dense representation that you can see here to overcome this issue. By segmenting fast motion areas and adapting the processing in real time, we can create a representation that is compatible with standard deep networks and AI models for segmentation and SLAM. These dense representations are essentially allowing us to integrate event cameras with state-of-the-art models in VLAs and VLMs, wherein you do not need to train them from scratch on event streams, but can actually use a little bit of fine-tuning to actually make them adaptive to this kind of sensing medium. So with this work, we were able to show that we can achieve a 1.5 millisecond latency closed loop for the perception with an approximately 2.7 times faster throughput than existing approaches on edge computing devices like a Jetson. This allows this fast perception capability to translate to resource-starved embodied AI and robotics that are going to work in such an unstructured environments. Another aspect of unstructured environments, it's uncertainty, right? So when you are perceiving through any sensor, current models are taking that each state or each sample with almost a similar amount of trust. With event cameras, we can perceive the world faster, but how do we know what we can trust? We use stereo event streams, as you can see here, much like stereo RGB cameras, to infer flow and depth of a scene to build a model. But there can be regions in a stream or an image where the region was only partially observable, as you can imagine like sides of a chair that are not clearly visible to you. But perception systems today do not account for such edge cases. They treat the whole image equally, which causes downstream issues when you're trying to plan around or trying to plan manipulation or path planning around that object or to that object. We counter this by building an uncertainty-aware system that computes per pixel uncertainty through an uncertainty-aware mask. So combining the event streams for each pixel, we will analyze that stream through a series of covariances, and that will give us a metric or a quantifiable metric to calibrate what is the uncertainty of that particular scene identifying regions where the system needs to remap, or we need to go back and learn more, or basically identify regions which the robot or the embodied AI needs to avoid when it is planning a certain task. These uncertainty masks are informing the downstream planning models for regions to avoid, remap, resulting in a 140% better flow and disparity prediction over current baselines. This system also creates a foundation for more adaptive multimodal systems where we can combine RGB, LiDAR, and event vision all together to create a robust stack that can switch leading sensing modalities as the environment changes. So, for example, you're going from a room to the outside. You do not need to program the robot to actually choose which modality to care for, but you can, on the fly, in real time, compute which modality is leading to lesser uncertainty in that particular scene, and then trigger downstream change in your planning. So this can modify the weights associated with each input in real time, leading to better assessment and modeling of the environment, wherein then you can make much more confident decisions of planning the motion of the robot and also interaction. This also has direct implications for downstream VLA pipelines and reasoning agents, because then they can confidently assess what is the environment that they're looking at, and then do this chain of reason planning for making better outcomes or better decisions of how the robot should move. Some applications of this work has been in animal sciences, where you're not only in an unstructured environment, as you can see here, but you're also dealing with a very unstructured and uncertain being, right? So here we are trying to introduce a robot to a cow so that it can monitor their health and well-being in real time. By analyzing about 36 points on the body of the animal, we can guarantee assessments of its health and behavior studies. And this is the first such work that can actually accommodate a lot of different conditions without needing explicit reprogramming. Building on this work this year at CVPR, we are also releasing this data set, which actually works in a very degraded environment visually in a barn, analyzing interaction and behavior of various animals without needing explicit reprogramming. And these are useful for not only farmers, but also animal scientists to actually study behavioral cues that can point to group health, productivity, and overall animal health as well. So putting this all together, today I presented perception in the unstructured environments, quantifying uncertainty to make better and more robust autonomous agents. Next is the integration of this uncertainty with multimodal sensor streams for cross-modal generalization into reasoning and visual language action models. I believe this work will improve the true robustness of current systems, enabling them to tackle more challenging environments. With that, I'm seeing my time and I'm happy to take any questions.
Thank you, Dr. Khan. Very interesting presentation. A few questions. One is, why are different perception systems even needed? Human beings can handle unstructured environments with just our eyes, right? Like, so why are these different perception systems required?
So that's a great question, right? Because think about how many times human beings also fail in unstructured environments. Like you're walking in a field and a spot is muddy and your shoe gets stuck in. And because it was covered in grass, you cannot just tell from vision that that field had changed, right? Or if something urgently runs in front of you, you're not able to accommodate your behavior to that emerging threat or emerging situation. So by expanding the perception capabilities of what human beings just have, we can make robots that are much more reliable and more robust to these unstructured environments.
Thank you. Another sort of related question is like event cameras or new types of cameras is one way to fix some of the perception problems, but can't we use like techniques like dead reckoning or some similar sort of techniques to sort of like bridge the gap? Like, is it necessary to move to new cameras?
I think a lot of it is dependent on the environment that you're building your system for, right? So if you're in an urban environment, for example, a classroom or an office space, where motion is much more structured, the lighting is going to stay at always going to be the same, and people are not moving as fast. There's no dynamics. Then of course RGB is reasonable enough to use, right? And you can build a map and reuse that map over time. But if you're in an unstructured environment, for example, a farm where things are changing, or a construction site where things are changing constantly, right? They're going to evolve over time and not necessarily according to some plan. You do not have that map of what it's going to look like in an hour or even in a day and so on. So in those environments, it becomes important to think about from the ground up, right? Of how are you going to create systems that can work with that much uncertainty in the system.
Got it. Yeah. The next question is, how do we systematically establish the generality of the approach to ensure that this sort of works across different types of unstructured environments? And when we are dealing with issues such as occlusion, or things like that.
Right. So the uncertainty aware approach is essentially like a mathematical way of creating this generalizable framework, in my opinion. Because if you can quantify the regions that you do not trust, or essentially an entity in the environment that you do not trust, then you can create better reasoning models that can overcome that, right? So if something is partially occluded, you can then kind of move your robot in a way, or create a path that will help you get more information if that entity is critical to you. So that kind of reasoning is something that humans do by themselves, right? Like I think some of the talks earlier mentioned of, doing these test cases of, getting more information about objects in your environment. So by quantifying this uncertainty as like a metric into your downstream reasoning models, you can then kind of automate this cycle of, I need to get more information where needed. And then you can also think about, extending the perception stack based on the environment that you want to build the system for. So whether that's event cameras or other modalities like tactile for manipulation or and so on, that can give you much more quantitative data of which modality is the most important for you in that particular environment.
Got it. Thank you, Dr. Kaur, for a very interesting talk. And definitely, I think this is a future direction to keep our eyes on. Next, I'd like to welcome Dr. Ashutosh Saxena, who is a renowned AI researcher, educator, and entrepreneur. He, after completing his PhD at Stanford under Dr. Andrew Yang, he served as a professor at Cornell. Dr. Saxena has built an impressive career spanning across academia and industry, co-founding several successful companies. He is highly decorated researcher with over 20,000 citations and recipient of numerous prestigious honors, including the NSF Career Award and 10-year Lifetime Achievement Award for his work in multimodal AI. Please join me in welcoming Dr. Saxena.
Hey, thank you for the introduction. Looking forward to the chat today. You should be able to all see my presentation, right? Perfect. So we're all here about physical AI, and as physical AI is getting very, very interesting. But I thought I would make a counter argument to this decade of AI, which is that for physical AI, we are changing our mindset at this decade. Everyone thinks that data is the problem, but data is not the solution. I'll talk about that today. Thank you for the introduction. I think I've been in the AI area for almost 20 years. Wrote the first paper on CNNs for robotics around 2009, 2010. We built a robot that can unload dishwasher back then. I built a project called Wikipedia for Robots uh, uh, in around 2016. And I've been now building AI for robots at Torque AGI with team from with engineers from SpaceX and numerous other companies and engineers who have built the foundation models recently. So today I will talk about that. Obviously, this is why many of us are here. That physical AI is making robots smarter. But the point I will make is that data alone fails because physical AI is not the same as digital AI. They're very strong parallels, but they are different. We'll talk about how physics can help and some examples of what we have done and put some robots to work. So I think when we build any kind of AI, I have been building that in the research world, in the enterprise world. The last decade, the way we built the AI was collect a lot of data, and for each specific task, find a model or build a model, train the model, and that will do a specific task. So that was the playbook. This decade, we are all excited because once you build a foundation model, now you, instead of building it a new application from scratch, you can pretty much throw the old playbook out of the window and say, hey, now I can take the model, prompt it in a certain manner, and build completely new applications. So one model, 100 applications, one model, 10,000 applications. That's what last couple of years have shown us, right? And that is also changing at companies like Waymo when we go to the physical world. So these Waymo cars, for example, or any self-driving car company used to have anywhere from 400 to possibly 40,000 small models. So think about one model detecting stop signs, one model detecting pedestrians, one model for highway lanes, and so on and so forth. And there's this orchestration layers that people were building. But now in that world, people are switching over again to one model that can do many things, right? Now at Torque AGI, we are doing that in enterprise robots. We love that area because we see a huge potential in a couple of different verticals there. But again, I think the playbook is similar so far. One model, many robots. But the key difference in digital AI on the left and the physical AI on the right is when we built digital AI and wrote all these papers, we were sitting on massive amounts of data. So when a couple of these companies started building these models like OpenAI, they did not said, oh, I'm going to digitize the information and build the internet. That was already built over the last 15 years. This is a very important point. So in physical AI, we do not have that luxury. So however, in physical AI, what we have is something called physical information or constraint. So we live in a spatio-temporal world in which things move forward in time, things are causal, and that makes a big difference. In digital AI, you're comparing documents. For example, using cosine similarity vector, whether one document is similar to the other, and that essentially makes, or some form of that makes the loss function inside the transformer architecture, right? But that does not make sense for robots because that does not capture the physical constraint. So that's our philosophy, that's our thesis. When we wrote one of the papers back then in 2013 on something called deep MPC, we brought the deep learning data-driven approaches and the guarantees of model predictive control into one model. So that's our way out to address many of these challenges in such models, right? So for example, we have been working with humanoid companies. We have been working with construction robots. Construction is a very dull and dirty environment, a lot of dust, so human beings don't want to do it. Automotive environments are dangerous. There is metal. And on the right-hand side, you are seeing a robot from a company called Dexterity, one of our partners. And these are large robots. moving and hauling heavy boxes in the environment. Throughput and timeliness and reliability is very important. So one common theme across these verticals is, and which is a little bit different from academia, your starting point is 99.9%. That's when people want to talk. So you can make one failure out of 1,000, but that's not the end. Then you have to push it to 1 in 10,000, 1 in 100,000. That's when you are actually building a business. A research paper you can write with 90% performance, and that's seen as a successful research paper. But that's actually a proof it doesn't work in industry. It's quite obvious, but also sometimes we brush it under the rug. So in our foundation model that essentially uses physics as a reasoning engine inside, that one model, through building onboard agents, we are reinterpreting the online agents in terms of inside the robot agents. Some other people are doing it as well, but these agents become specific for each robot. So you could be putting the boxes on the left, comes on a conveyor, the robot picks it up, figures out how to stack it, a lot of perception, a lot of reasoning, a lot of motion planning has to go in there. On the top right robot, you're looking at a painting. Now, if any of you have ever done any construction work in your home, you would realize how complex and messy it is. And it's very hard to make a flat drywall. You are doing very nuanced perception, local control, and touch tactile feedback when you are scrubbing it. And then moving on to humanoids, which is more of a development exercise for us right now. So this is what the foundation models can generally allow us to do. I will tell you a story of what we did about 10 years back when we started building such kind of models. So this paper won Best Paper Award at CVPR 2017, followed by Robotics, Science and Systems 2023. And here is what we did. We took an insane amount of data from online world, right? Like images, videos, robot action, all publicly accessible. And this was the first paper that showed that you can actually take entirely different modalities of data. Could be images, could be 3D, could be text, and they all map into the same space in the machine learning architecture. And that was very exciting because the reason it is very interesting is you could be using LiDAR, you could be using a completely different robot, but if they map as the same thing into the knowledge in that area of the network, that shows that now you are learning concepts, not just rote memory. And this was the kind of, we didn't name it VLA, but follow-up paper cited this to call it the vision language action models afterwards. And this kind of model was able to do several things. Let's focus on the right-hand image. Once you give it sufficient amount of data on that particular task, it's able to integrate it. It's able to do things like cutting different kind of fruit items. And that's very exciting. It can even fold boxes on the left-hand side. So we tested it on hundreds of different tasks that you commonly find in the environment. So we also collected bunch of data by going to students' dorms. So we have our lead student ran a whole exercise at Cornell University collecting that data, and we showed this to work. So we were very happy, but what we also found is this is still data-driven learning. This is still data-driven learning. When we gave it situations like this, hey, I'm now showing you a couple of examples of pouring and making cereal. Couple of examples did not teach the robot enough. There was enough variation. This is one of the more obvious ones that, oh, well, a human would have thought to open the cup, but there are also, for robotics people who know what is going on, there's also a lot of nuanced variations. And by the way, I'm a big fan of real environment. So when you go to a warehouse, when you go to agricultural field, these are dirty. This is one of the cleaner examples, but this is still far better than white tables and red blocks, right? So often people underestimate that. But this variation is like, why is it not learning? And then we also saw one of my colleagues, Henny Benamor, who wrote this table tennis work, who was at Google DeepMind, they spent, I think, over 100 million. I think the number was closer to 220 million that they spent to collect this data to then show that you can open Office drawers and do a couple of tasks. Things have gone slightly better, but the problem is none of the people have any idea today how much data we need to get functional robot that is being promised by the people today. So there are some instances, but they are very narrow. If you're an insider in robotics, you will realize how narrow they make it to make it work. I mean, the things have improved, but to make a real model in just brute force data manner, no one knows whether it's 100 billion of data. That's, I think, the floor that people think, but it could also be $1,000 trillion in today's dollar amount, right? And let's not underestimate when OpenAI started in 10 years, 12 years back, they were sitting on a massive amount of online data and library books, right? But solution, we cannot be collecting this data. So what we have done at Torque AGI is one of my, on the research level at least, I'm a big fan of Jan LeCun's work, right? We did a project together back in 2004. And I think intuitively, the LLM is trained on a massive amount of data, but a child is not. And another way to think about it is that an AI is at worst 10 times worse than an average human, but not a million times worse. Not a million times worse. So if you really think about what is going on in physical AI approaches today, it doesn't make sense to me. It's like, why are we collecting million examples of some robotic task and showing a demo? We're still not reaching that level of intelligence. So the problem is somewhere else. So what we have been doing is injecting and building models where at the core of the model, at the attention level, at the inside the GPU level, we have really incorporated appropriate loss functions, appropriate operators. These operators are inside the model. So instead of trying to think and output something and you at millisecond or second level, you are trying to correct it, the model just doesn't even look at scenarios which are not plausible. So what that does is that learnings from same idea, but learnings from an entirely different robot could transfer over and go into the same model as a robot and as a large robot, which is a large equipment robot. And one of the talks earlier today in the day mentioned the use of calculators, for example, right? So while the earlier LLMs did not have that capability, but the more latest ones, or if you use Claude, for examples, they use skills, they use operators, you can name it in many ways. But if you ask it to do 1 plus 2 plus 3 plus 111, it's no longer using LLM, it will fire up an internal tool, right? So same thing we need to do in robotics at the internal level. Then obviously, there is the whole element of how do you make it fit into a GPU, because the robots that we work with, they work in a warehouse which is made of steel, so you don't have internet inside, or they work inside a mine or inside a tree scrub. And that's where some engineering comes in, where you have to really think about how to make the data and thought happen both in the GPU. Agents are really orchestrators of the thought and the data together. So that's how you achieve millisecond level performance, which is really necessary for real-time reliable performance. So there's a lot of engineering that we are doing in partnership with NVIDIA. And that is how we have been able to put some of the robots in production. For example, this robot only took 300 demonstrations. It was a little bit unbelievable roughly mid last year that we could actually do that. But this makes us very happy. We have been putting robots to work and in different environments. For example, in agriculture, where tasks from crop identification, weed identification to certain implement related tasks, solving end to end. Basic things like figuring out if the robot operate. These are some of the hard problems, safety related problems. So I think on the left one, some of you can see there is a human there. On the right one, humans actually fail in comparison to the model. The model performs better, at least in this narrow use case. This is some of our other partners like Dexterity, where the robot handles boxes. Boxes are very difficult. At December end, you have red boxes. Sometime around mid-February, you have pink boxes, shiny ones. These things get difficult for the robots. You have kidding. There's a whole lot of warehouse tasks. There's a whole lot of QA tasks in warehouses. So what we are doing is we are building a master model, and then when we bring it to the edge, there are certain specific variations. So Flow really cares about latency because that robot has to work fast in the warehouses. Build has to worry about precision and feedback loops during the build process. Field has different properties because it operates outside in the environment. Inspect is kind of an add-on to the rest of the models because you might as well inspect the fruits, inspect the build, or inspect what is going on. So to wrap up, I think what we are doing is building physics reasoning models that are driving numerous applications across the world. Just make it very exciting because then we can have the model adapt and make it. Thank you.
Thank you, Dr. Saxena, for the great talk. Very interesting. A couple of questions here. Like, one is how much physics is actually required to get these models to behave well, and how are the physics priors like given to the model? Is the model like allowed to infer from the demonstrations, like what's the physics behind it, or like is physics explicitly given as a prior to these models? Like,
there are three different kinds of physics. One is laws of the universe physics, which is that things are causal, things are spatiotemporal, things like gravity, which most of the robots have unless you go to space. That is in the structure of the model as we build. I don't think we want to learn that from scratch. If you want to win a Nobel Prize, we might in academia, but not to be practical, right? There's a second type of physics, which is robot dependent. It turns out that every single robot partner we worked with, they have a very micrometer level precise model of the robot on the first day one. So that you can learn, but then you are having roughly 10x to 100x data inefficiency. So we just give it as the first instant. Then the third category is a approximate physics, which is a combination of things like object permanence, locality, like two objects can go on top of each other, contact physics. So those are modeled as a data-driven model, but that's a separate aligner versus just raw road memory. So this kind of approach, that's what gives us 1000x data efficiency.
Sort of a related question that's coming, like, it's pretty complicated enough just to use Newtonian laws, but what about computational fluid dynamics, Navier-Stokes, Bernoulli, etc.? Are these all like baked into the foundational models?
No, so that one I would call it as the approximate physics, which is the third category. So what generally happens, you want to have a separate part of the network or an attention function or loss function that caters to that, but we don't want to specify it perfectly because it's not going to be exact.
Got it. So I mean, I think in terms of like the real world, the deployments that you've seen, right? Like, what have been the challenges? Like, what have been like the common failure modes?
I think there are kind of three levels of difficulty one can talk about. One is often we see in a laboratory environment, which is a good start, that you have a perfectly laid out table, you have reasonable lighting. The second one is a typical operational environment. So think of a tractor going into the field from 10 a.m. to 2 p.m. Or in a certain type of a warehouse where things are nicely laid out. Those do unlock some of the use cases. But when you start going into the real world, this is actually a nighttime image on the right, highly grainy. This is not even an edge case. This is what happens when tractors work. In Midwest, in October, November harvest time, or whenever it happens, it's dark, it's dusty. In mines, every randomly the copper mine would change its color every second week because copper is one of those minerals that changes colors. In warehouse, people move things around. Boxes, think about how many shapes of packages that you get in your home. That amount of variation, and when you, especially when you're talking about 99.9% plus, because this robot, if they're working on an 8-hour shift and they are handling every 2 seconds one package, as an example, in 99% it is still interrupting quite a lot. It's like multiple interruptions per hour. So that's what you're dealing with these kind of machines.
Now, the final question, I guess, are these models like deployed on the robot, or is it deployed on the edge? Like, is there some sort of edge server that you connect to, or does it depend on the different kinds of models that you talked about?
These are all deployed on the edge. So we have built a distillation process, which actually in partnership with NVIDIA. So you are doing a heavy duty mixed precision quantization, truncation of networks. Most industrial robots don't have access to reliable Wi-Fi, and that introduces latency also because decisions have to be made in 30 milliseconds max usually. So edge is a requirement.
So by edge, is it like physically on the robot, or is
Physically
it like
on the robot.
Oh, it's physically on the robot. Thank you.
Yeah, at the 99% of the cases, 99.9% of the cases, you have to have it on the robot because otherwise it's operationally very difficult to maintain compute separate from the robot.
Thank you so much, Dr. Saxena, for a great talk. And yeah, now it leads up to the panel discussion. Ramana, please.
Thank you, Jen. Thank you for all the, to all the speakers. I mean, it's been an amazing set of talks that covered, I think, a wide gamut of topics, ranging from world models to, 3D to, I've heard 4D multiple times, and real world use cases, physics. I mean, it's just a pretty good spectrum of talks. So I think in this panel, it's my pleasure to have, 4 speakers that have already given talks. Dr. Bolei Zhou, Associate Professor at UCLA. I think it was one of the first talks, and followed by Dr. Achuta Kadambi, who's also a professor at UCLA. Talked a little bit about spatial intelligence, and Dr. Rupinder Kaur from Purdue. She works in cyber physical systems, and she talked a little bit about some of the perception and new types of cameras that can help with improving perception, stuff like that. And finally, Dr. Ashutosh Saxena, who's from Talk KGI, gave a wonderful talk. So welcome all to the panel. All right, so I think the panel discussion I've sort of like broken down into 3 major segments. The first segment is around, I just wanted to understand a little bit about the state of the art in terms of like, what are the biggest bottlenecks around embodied AI today, right? So, I mean, there's quite a few bottlenecks, right? There's model, capabilities, there is data, there is, sometimes you have to resort to simulation. I mean, there's just a lot going on in the embodied AI world. I think maybe this is actually a question where I'd go to each of you folks to actually give me a little bit of clarity on where you see the biggest bottlenecks are. Maybe I'll start with Ashutosh because he just finished his talk, and maybe as a segue, really where is the real big bottleneck? I mean, is it actually in the physical modeling? Is it actually in the data? I think you touched upon it in your talk a little bit around how data is the problem, but data is not the solution in a way. You want effective models too, but I really wanted to understand where exactly you see the big bottlenecks, apart from data, of course, which is usually a big bottleneck for pretty much all the research in these directions. But where else do you see big bottlenecks in advancing the field of embodied AI?
So a couple of things are really amazing now. So simulation helps at the very minimum in testing and early rejections of obvious bad cases, right? It was difficult to build earlier. Now it's much faster. So that's how we look at the simulation as a little bit of data augmentation, but more about a very powerful uh, testing environment, which is very important for robotics. Robotics has also matured in having some amount of data, real world data. The problem is um, AI models today or over the last 5 years no longer benefit, at least the frontier models, from large amount of data. So if you're collecting the same example 1,000 times, it could have helped a convolutional neural network like approach 10 years back, but it no longer helps the model. So diversity and richness of that uh, data is very important. And to tell a story, one of the vice presidents at Waymo is our investor. We hear this is public information, right? Like the data that on a unprotected left turn in San Francisco, there was a car that ran through and then Waymo had to take a turn. That data is worth 5 million, that single instance. And they have to wait years or months to collect that instance of data, right? So that's how you look at the data. So same thing goes in physical AI for us. It's like, how do we get those experiences, those nuances in the world without needing to collect everything? So at least at Torque AGI, we think that some of that is known. Like you don't need to have a data that you cannot fly in Denver. A ground robot cannot fly in Denver if you know that it cannot fly at all, right? That's an exaggeration, but you can, just to make a point, right? So obviously the models of physical AI have split into two different worlds. The robotics community knows how to do geometric motion planning and very good models. And then there is the data driven approach in which some people have thrown everything outside the window and fed the tokens into a model and see what it does. I think the right approach lies in the middle. So that, to summarize, I think there's great win in simulation, great win in energy in the field to collect data. But from my point of view, building physical AI the right way, we need better model approaches.
You might be muted, Ramana.
Oh yeah, thank you. Sorry about that. Maybe the same question. Thank you, Ashutosh. I think same question to Bolei. So Bolei, I think given your operational experience around these Coco robots, right? So what do you see as the biggest bottleneck for you to be able to push the envelope from, I don't know, 80% human teleoperated to I would say 99% AI operated, right? So that's the world that we want to migrate towards. I mean, you outlined a few challenges, but I mean, are these fundamentally unfixable, or do you just see, over time these models getting better and better and the pendulum swinging more towards the AI side?
Yeah, thank you for your question, Ramana. I think there are a lot of limitation there. I think a lot of the embodied AI for physical AI companies are still at the stage of doing like in-house demos. So when you deploy those bots in the real world, then there are a lot of corner cases, right? So Coco right now is running the robotic fleet, like hundreds of fleets all over different cities. Then there are a lot of corner cases, people walking on sidewalk, people sleeping on sidewalk, right? A lot of corner cases. So I think one challenge here is how we evaluate the autopilot model before the real world deployment. This is also related to the model comparison, right? So we have so many humanoid companies. They all have a different humanoid. Then how can we fairly compare their capabilities, right? So it's quite difficult. Usually when people train their autopilot model, they will train on the offline data. But in the real world testing, so it's an online case, right? So then how can we fairly evaluate the autopilot model or the different robotic policies and compare them and benchmark them? It's quite a challenge. I think this is an insight also shared by Jitendra Malik several, like I think last week. He mentioned that many robot companies, they are doing the demos, but how to compare their policies in the fair ways so we can measure the progress, right? So I think that's a limitation there. Like we can definitely use the simulation for comparison, but there is a this kind of a real to thing gap, like visual appearance, and also the physics is not as accurate as the real world. So in the case, how can we have a real world settings like test bed? I think that is something we need to think about and come up with.
I mean, I guess in some sense it has a lot of parallels with autonomous driving, right? So why is driving a relatively easier problem than, food delivery carts on the sidewalks? Is it the complexity, the richness of the environment? Is it actually substantially more complex than what like cars usually see on the roads, or
Yeah, the cars on the road usually there are only road structure and the roadside. There are not people, not so many people like walking on the road or jaywalk, right? So, but for sidewalk, people walking on the sidewalk, right? So then how can we reproduce the different human behaviors and the different human activities in the simulation environment is still unsolved problems, even in computer visions. How can we learn to simulate different human activities and behaviors? I think we have a lot of progress here, but I don't think we can reproduce all kinds of behaviors there yet.
Can I add one comment? I think it really goes down to what is the performance expectation level. So if a autonomous car has an accident and if it happens more than once in 63 million, DMV or insurance company gets very unhappy in addition to the general public. But if you look at the delivery robots, we all laugh at delivery robots hitting people, poles, getting stuck. That might be actually one in every 1,000 hours or maybe one in every 100 hours, and people just help the robot. So it's kind of also dependent on the application.
Yeah, that's fair. Actually, which is an interesting segue to maybe Upinder, because in your domain, Upinder, I think I guess you deal with unstructured and unpredictability all the time. So I guess what are the real bottlenecks in your domain? I think there's a lot of parallels to some of the things. I guess Ashutosh covered a little bit of the robotics in enterprise settings and Bolei on the delivery side. But I think your world is also pretty exciting and interesting and unpredictable in its own way. So I would like to also understand maybe what the bottlenecks there are.
Yeah, I think as the other panelists mentioned, right? So you can get a few videos of like a car driving and then use it to train your model, but how do you get a video of a cow interacting with a robot, right? I think that's the first video I took, and so on, right? So the unstructured world, whether it's highway mowing or working in construction sites or on farms, is very unpredictable, and no two spaces are alike, right? So a road in Indiana is, I think, fairly similar to a road in California. Might be just less crowded than yours. But a farm that's neighboring to two farms neighboring each other can be very different, right? And then animals on top of that are individuals that you're dealing with their own sense of, subjective sentience. So how do you model that into something that's that especially we as human beings don't understand what they're thinking even now, just from cues. So you can have a lot of data, but as other people have mentioned, like, is that data really going to help you accomplish this task, right? Which we have seen it doesn't as well. So I think the quality of data is important, but then also creating these models that can handle the uncertainty, right? Whether it's through retracting when you see something that's going to attack you, or whether it's through expanding your perception space so you can possibly get more data points of the same environment from different views, and then make much more better informed decisions. So I think the answer is somewhere in the middle where, the physics will have to catch up, and then we have to have algorithms that are looking beyond this closed set of just perception and our own like human-driven thinking to actually look at more of a first principles approach where you cannot rely that the human is making the right decision here, right? So I think that's where, at least for the unstructured world, I would say where the field needs to go.
Same question to you, Achuta. I think this is, I would love to hear different perspectives. And Achuta, you have the spatial intelligence as yet another weapon in the arsenal. So you want to tie that back into this, and how to actually really overcome the various bottlenecks for embodied AI to become real, and how it actually sort of complements some of the things that folks have already touched upon.
Yeah, I think the privilege of going kind of last is that I think it's been covered by the excellent panelists. I think I want to reinforce a little bit of Ashutosh's answer in the beginning, which is that there's a common perception amongst operators, both in my previous companies and the university, that just pumping more and more data is not going to get us to the embodied AI that we want. And I think part of that reason is because there's a lot of physics and structure to these problems that can be leveraged. And so if I were to maybe add something a little bit new to it, I would say one of the interesting challenges that we're going to face, I think there's a great opportunity for new startups and students and practitioners to actually dust off some of the algorithms that are 20, 30 years old and bring them back. Like a lot of these left and right problems that I was talking about in my presentation, you could actually trivially solve that with sort of like an optical flow, right, or coordinate-based transforms. And so what we discuss internally in our group at UCLA is that we kind of see a lot of this as the calculator. We're trying to find the calculator app for physical AI. What does that mean? LLMs deal with numbers all the time, right? You want to do a whole bunch of things, you will need to add numbers. It took a couple years. People looked at all kinds of crazy things to get numbers to be added with tokens. Like, they had some great papers on reverse lookup, flipping the string, flipping the latent space, but they could not get numbers to be added precisely, which is a big problem if you're crunching spreadsheets and doing a lot of things. So eventually these model providers said, okay, fine, we'll just call the calculator app and then let the calculator handle things when numbers come in. So I think there's that type of integration that's going to happen with physical AI, where we're going to go back to dust off old robotics textbooks, come up with a calculator app from those old textbooks, and then call those with some of these systems.
Yeah, that's a good analogy, actually. I think the right tool for the right job, right? So it's not like, you can take a wrench and use it to screw a screwdriver or something. I mean, you really need the right tools for the right jobs. And I think part of the fixation around these models has been that you are trying to crunch a lot of capabilities into one model or two models, and they're not. It's just not easy to build a Swiss Army knife of models, right? So I think this is where I think some amount of specialization around rightfully identified depends on the task and depends on what you're trying to actually accomplish. Breaking it down into sub-components which are modular and stitching them together in a fashion where you can leverage the right module for the right task, right? I think that is the way I think scalably going forward is what I'm hearing. And also simulation and figuring out those corner cases, making sure that you kind of anticipate or cover the ground in a systematic fashion even before you deploy your models, especially when you take these from research to putting them in the real world. I mean, even if you look at autonomous driving, right, people have talked about autonomous driving since 2010, 2011. You've already seen Google cars moving around, but it took almost 15 years for it to actually get to the level and degree of stability required. Even now, I mean, there's of course issues, but far, far, far less than what it used to be 15 years back. So I think it's really the last mile of engineering systems, robustness that we, and all the tricks of the trade that you guys have talked about that need to come together in order to probably tame the beast. But quick general question. Anybody here willing to sort of put a prediction on when exactly the ChatGPT moment for physical AI is going to happen? Is it 1 year, 2 years, 5 years, 15 years? Any take? Nobody wants to go? Nobody wants to put a number?
I think depends on how you define robots, right? So in some sense, it has already happened that at least a couple of companies, including us, are taking a small segment of robots, a class of robots, and putting it into production. But this is the beginning. There is a lot more to do. On the flip side, I think there's a difference between making models that can drive multiple robots versus humanoids that can be deployed and start actually working in the home. That I am more siding with some of the other people. They're probably going to be around 2040 or 2050. So my answer depends on the definition of the robot.
Fair enough. Which sector actually do you think the robots are? I mean, of course, we've had robotics for like past 20 plus years, right? So I think what I'm actually more going towards is this marriage between, VLMs and VLAs and world models and those kinds of capabilities that these models have unlocked, right? Leveraging them to do general purpose, not fixed function like an arm assembling something in an assembly line. I mean, that has been around for decades now, right? So that's not the fixed function robotics is not really what I'm after. I'm really after the more general purpose, teachable, trainable, interactable, those kinds of stuff. And it could be in certain settings. It doesn't have to be like, home settings. Home settings, like you said, is, I think, even if the capabilities are there, 90%, 99%, you really need that 5.9, maybe even 7.9 reliability in order for you to sort of embrace robotics in your home. And that will be I don't know, it'll take probably a decade or two. But what about in settings like enterprises, right? Warehouses are a little bit more restricted, but maybe even in corporate enterprises or things like maybe, I don't know, making some coffee or mixing cocktails. You see that routinely in malls and stuff these days. Are these environments actually, do we think like more general purpose robotics can actually enter into these somewhat limited domains in the next like 2 to 5 years?
I can go again unless someone else wants to answer, but I think people underestimate the amount of complexity or the search space when you go from a smoothie making robot that is in a glass environment behind a wall. It's going from fixed places to a barista who has to make coffee in a coffee shop. It's like we're talking about several orders of magnitude increase in complexity. It's like uh, you can even mathematically probably write it down, right? So when things are constrained, what we are already seeing is going from entirely fixed assembly lines to some amount of variation. It's happening. It's already getting deployed, right? The next level is, can it operate in warehouses? That's actually a little bit more unconstrained. To go all the way to, can I just have a robot that can literally accompany me and do everything that a human does, or many of the things that a human does, which some of the companies are projecting? That will take time. I think that's kind of my opinion. Time means I'm talking about 15 years plus for the last one, right? But the first one is already here. The first one was warehouses, reasonably constrained. If I can explain a SOP, okay, do this, but don't exactly specify and set up the environment. That is doable today. But otherwise, the scope is, we still have to solve a lot of problems for the full scope.
So, I kind of touched upon this before, but models, I mean, in the normal cloud world, large language models, we kind of take hallucinations and we're like kind of, okay, fine, AI makes mistakes is the common tagline that you see underneath pretty much all of these frontier models, right? And it sometimes makes mistakes. Okay, thank you. Can we accept this kind of a paradigm for robotics, especially if you have like a Unitree, I don't know, 200-pound robot humanoid? Sometimes it hallucinates and bumps into a person or a child, even less. I mean, these are kind of like it's not it's not the same as like a Gemini or OpenAI giving you some false information about, I don't know, some field in a tax form compared to like a physical robot hallucinating and doing something pretty dangerous. So how do we actually I guess this is a multifaceted question, right? So how do we ensure that hallucinations don't creep in? I mean, there's no way, these are all probabilistic engines at the end of the day. Humans are prone to hallucinations. Heck, I mean, we ourselves sometimes get disoriented and run into other people, right? We say a sorry and move on. I mean, is that acceptable for a humanoid to do? I'm not so sure about that. So I guess maybe this is a very generic question, but we can sort of take the lens of the particular environments that you're looking at and map it to what it means to have hallucinations in the particular environment. Maybe I can start with you, Upinder, in the kind of environments that you see. What are the ramifications of hallucinations and what type of mitigation steps can one take to ensure safety in your environment?
Right. I think in our current work, we have been benchmarking some of the VLA models for a simple navigation task, right? And because it is kind of imagining the next step, just going down a corridor, it creates a zigzaggy pattern. Now, if I submitted that answer as like a robotics student to my professor like 5 years back or even today in traditional robotics, right, where you do that through algorithms, I won't pass that course, right? And that is just down a straight corridor. So when things get more complicated, especially when you're moving around different objects, which are both static and can be dynamic, this becomes even more complex, right? And part of the reasoning in what we can tolerate as a failure, like, okay, can I take in a zigzaggy robot that still gets me my coffee? Sure. But can I take a surgical robot that's going to create a zigzaggy cut? Possibly not. So I think it depends a lot on the application, right? So when it is, and especially with the sophistication we are expecting from the end user, right? So if it's a roboticist that you've given a robot, they have a much more realistic expectation of what this can do. But for the general public, they are going to expect more, and that is something we are seeing in the house cleaning robots and the lawn mowing robots. Where if you look at the comment section of the product, there are a lot of things that they are saying that these are they're failing even today. When we talk about the unstructured world, these becomes more critical, right? Because you cannot have a robot shut down construction on like a $2 million building for a week just because it slammed into something. Similarly, with, I would say, in the agriculture domain, like especially with animals, it could basically kill like an animal if it were to go rogue or perform incorrectly. So I think in those domains, especially for a certain task, it's a much higher bar to clear. But if it's like even in the home environment, if it spills the coffee on you, are you going to trust it the next time? No, right? Third-degree burns. So I think it is much more task specific as well than just domain specific. Like we can take a few errors in monitoring, but we cannot take errors in interaction, or especially physical interaction. The other thing is that there have been cases where robotics has proven to be much more reliable than human operators, right? For example, there's a paper a few years back where they showed for some eye surgery, the robot was much better and it had less variation in its performance than even experienced surgeons. But from just a variance perspective, robotic surgery is not fully automated even today, right? You always have a surgical team on place. So I think that might just be the way to go, where the human is still present, but is not actively doing all the tasks in the short term. As we learn to incorporate all these different nuances that you might miss in the initial development of these models.
But in terms of mitigation techniques, how can you actually, I mean, is just testing and more testing and more testing, or like what are some of the, foundational research building blocks that you can put to make sure that, I mean, what type of guardrails you can actually sort of put, right? Like
I think
which,
there are two things. One is adversarial testing, right? Where you're basically trying to attack the model and stress test it, right? So we do that for robotics because like the physical failure is very catastrophic. The other thing we think of is essentially making sure that the critical actions are always overserved by human beings, so that it can have the permission to go forward. And I think that also helps a lot in terms of building trust into these models. And it can learn sort of like online, offline when it's updating its policies. And I think that sort of interaction is important as we go forward.
Bolei, Achuta, please go ahead.
Yeah, I think, go ahead. Sorry, why don't you go ahead first? Yeah.
Go ahead, Achuta.
I just want to chime in, Ramana, on that point, if that's okay.
Yeah,
I guess
please.
everyone was excited by this question. So I teach in the electrical engineering and computer science, right? So on the EE side, I think it's fascinating to see what the people on the chip design side are doing when it comes to how to use Gen AI to generate their chips, right? Because if you tape out the wrong chip, no PhD for you, as an example, right? That's kind of the stakes there. But in computer, like in CVPR or computing, right? It's like you can get away with taking a model and then fine tuning it and then being 70% accurate on this. So I think there's some DNA that needs to change partly, where maybe the team here, we can all group together to create a new benchmark, right? David Patterson at Berkeley used to often say when we were undergraduates, right? He used to tell us, for better or worse, benchmarks move a field forward. And so if you benchmark in a way that you really say, okay, you cannot have any hallucinations, we need to be at 6 sigma tolerance, which when people start robotics companies, they then have to go into that. Customers are going to ask, okay, is this going to pass 6 sigma in its accuracy? And a lot of academics raise their eyebrows and they ask, what's that? What's 6 sigma, right? in computer science. So I think it's also part DNA and culture. And on the technical side, and I'll cede my answer here, but on the technical side, if there's ever a rabbit hole to go into, look at what the chip design people are doing with AI, how they use AI to generate their circuits, and that can give us kind of a blueprint a little bit.
Yeah, makes sense. Ashutosh,
I can chime in. This is a very exciting question, actually. So everyone wants to chime in. But I think I come from a world where I've seen research and now building things in industry, like some of you, right? And the worlds are different. I'll take this question from a model side. So there are actually ways to use statistical modules which behave statistically while still retaining guarantees. So let me take a layman example. While your car can steer in the lanes, a simple lane assist system, if you press the brakes of any car today, at least in the US, it will simply bypass every single function. If electrical failures happen, your car will still brake. It is mechanically coupled by law, right? So brake overrides everything, even electrical signaling. Now you can have a electrical assist. But point I'm making is, so when we are architecting these robots, we are working with some heavy equipment companies, right? Think about a very giant tractor, very giant machine. One way to think about that is called red, yellow, green zones. Not everything is a driving problem, right? A red zone means your traditional safety systems will act that way. Green means model says everything is great, go anyway. Now, yellow is where the power of the AI comes in, because you can now deal with 0.1%, 0.01% error rate while not destroying the guarantees of the red system, right? So that's one way to architect the system. The second way to start thinking about is on the uh, on like the design of the model itself. So when we were developing the deep learning and model predictive control layer, you are staying under the L2 funnel of this model predictive control, but within it, you are having a faster search because of the model, a more better kind of selection functions. So those are a couple of techniques where you can have guarantees. Now, obviously, testing and making AI better is one direction, but how do you merge it with the safety critical system is another direction.
Bolei, you want to chime in as well, because I think you have a
Yes, so one thing I would like to add about the mitigation of the model is or the robot is that how we place human into the loop. I think human is a very important contribution to correct the robot behaviors. Not just to put human inside, also think about how we design the system such that human can better or more effectively provide feedback to the robot. Right, so human not necessary to intervene the robot operations at the same action space like driving. Human also can like slow speech or slow the eye gaze. So there are this multi-signal that we can communicate with the robot and teach and correct their behaviors. So creating this kind of data flying wheel, I think is very important to have this continuous learning and continuously improving for the robot. One example is this Tesla, right? So they have this autopilot, then they also continue collecting the human interventions when the autopilot make a mistake, right? Those data are being used to improve the models, and the latest model then will push back to each vehicles, right? This kind of data flying well with human in the loop, I think it's a very important mitigation or continued learning methodologies for robot learning.
Yeah, this actually ties back to what Jason was mentioning also around how, humans and robots, come together to upskill. Humans help upskill the robots in a way. That's a very interesting perspective, right? So, but I think I mean, there's diverse answers, but I like the framing of this, right? So I think, first of all, robots need to know where they're confident and where they're not confident, where they need to cede control to mechanically coupled or human in the loop or some other system. So you can't just assume that the robot will just act upon whatever the model tells it to act on. Okay, there should be sufficient. Here is where I think the agentic paradigm can actually come in quite a lot, because that's something that we have not really touched upon, and maybe and some pieces maybe we touched, but the thing I like about agents is this personas of like a developer, tester, verifier. These personas actually are different ways of making sure that there are checks and balances in the system. So if you were to actually think of a robot having like a left brain and a right brain, one to keep a check on the other, right? Like a multi-agentic system, I think that would be a way to somehow at least separate the concerns, right? One wants to act, one wants to curtail, and both sort of together in tandem, sort of keep the appropriate checks and balances so that it knows when to not do something and when to actually do something. So that I think would be an interesting paradigm. So thank you. So there's a few, I think we're like sort of in the last section of the panel. I mean, we have about 15 minutes, but I thought I want to shift a little bit of focus from the architectural side to more policy side, and more regulation side, and I want to understand, like, if you were to actually, like, maybe spend some time talking about what type of hurdles do we see, first of all, from a robotics practitioner's point of view, right? I mean, and I think some of you and many of you have some real world use cases around introducing robots into the real world. Like, so what type of frameworks, regulatory frameworks exist today, and how should they be somewhat modified to accommodate for better experimentation? Because we will not get to the utopia unless we cross several hurdles, right? I mean, it took whatever DMV to grant a license to Waymo, I don't know, 15 years. It just it's a long process. But if you were to accelerate sooner, how do we, what type of whatever checks and balances exist in the regulatory system today, to how do we relax it? How do we, what type of changes do we need to accelerate this field forward? Maybe I'll start with Bolei, and going to other folks as well.
Yeah, so because right now I work with Corso Robotics, so they partnership with a lot of restaurants and the small size grocery stores, right? So they try to empower those restaurants, because if they can have autonomous delivery, people will order more foods, then they can earn profit and make livings. So when they move into some new cities, so usually they will use those examples to pitch to the city council to give the permit, because the city council care about the local restaurant can be better empowered and people can get happier, right? People can buy more stuff from the local restaurant, right? So that can create this positive societal impact. Because this kind of a food delivery also receives some like a criticism, like say the robot take over people's job. But I think the more positive side is about how we use robot and the service to empower the business, like the conventional business, right? So that is something we can think about.
Okay. Any thoughts here, Ashutosh?
I think it really depends. There are two levels of regulation. One is AI regulation in general. That's concept number one. But the concept number two is the target domain of the application. So DMV application applies because you're driving on public roads and it's very close to a human driving, right? So now if you think about enterprise robots, a warehouse actually has industrial regulations on the maximum impact of force that a machinery can impact on a human, and no one assumes there that you will come out completely safe or you will never touch an equipment. So as long as if we are able to guarantee that the robot's force impact on the human being is lesser than something, that's one example of regulation. Same things could exist in mining machines, agricultural tractors, and so on and so forth. So I'm always a big fan of look, the AI driven robots still have to function in that environment. So that environment and task determines the regulation, which in most cases already exists.
So are these part of the OSHA, not federal, but California, or like whichever state, OSHA standards, like workplace standards, like, where are you saying that, like, if the robot like malfunctions or something, it doesn't do it in a catastrophic manner? Is that something that, I mean, I guess the robot vendors, do they have to like certify, or, how exactly is this even verified? I mean,
No, so basically, let's talk about industrial, for example, let's take warehouse or factory certification area, right? So there is a committee, and there are two of them, one in US and one in Europe plus other countries, which are very similar. I don't remember the codes exactly, but they exactly specify, it doesn't matter if it's an AI driven robot or equipment, it should function in that manner, right? If it can cause very heavy duty force, it has to be fenced, period, right? Doesn't matter if it's an AI driven robot or not. But if it's a lighter weight equipment or machinery which can work in conjunction with humans, it cannot have sharp edges. If it moves, if it hits some arm, it's okay to hit, but you don't hit it more than certain amount of force. So if you are building a robot with AI, we have to put a hard limit on the maximum amount of force it can impact on a human being, right? So
But
that's
is
the
it
way
actually,
to.
but is that tested by somebody? Is there an individual testing, like separate company that verifies and makes sure that that is actually the case, or how does it work? How do you ensure that that is actually the case?
Is the company is supposed to self-certify and do it. 90% of serious equipment manufacturers actually get a private third-party certification. The government is not involved in literally certifying it. But it's like FDA, right? If for critical drugs, government may come in and test, but bunch of the other equipment manufacturers would self-certify and optionally get it third-party testing done. Like a UL certification, right? Like UL certification is basic electrical requirement that you won't get electrocuted. Manufacturer would certify, take appropriate precautions, and get sample checks done by a third-party certifier just because it helps the product be more reliable.
Okay, okay. No, makes sense. Makes sense. So the other, other question actually along these lines is there are obviously certain countries that are a little bit more advanced when it comes to embodied AI, robotics, compared to the US. Partly, maybe it's because of manufacturing, maybe because of regulation. There could be several reasons, but what should like state entities and and even companies and just everybody, right, in general within the US to actually bolster this kind of an ecosystem? What should happen? I mean, given that you've been at the forefront of leading this, is it more money from the governments? Is it more funding? Is it more relaxation in terms of regulation? I mean, just trying to identify how to actually, what are all the challenges? And that's on the more government regulatory side and maybe funding side, but also from a collaboration, open source, data collection, data sharing perspective, right? So that is another front, because I see people are doing their own, and I heard some talks around, for example, leveraging federated learning to actually take and world models in some sense, sort of unifying. There is a theme there, but I think it'll be good to sort of distill this into a few action items that I think collectively we should be thinking about to bolster the ecosystem. Of course, there are some which are probably outside the realm of academia and any one company, but like, for example, manufacturing processes. I mean, we don't have a robust domestic robotic manufacturing process. That's just the reality of it. Maybe apart from that, right, what else can we do to actually really truly improve this ecosystem? Maybe I'll start with you, Achuta, and
Thanks, Ramana. I think great question. I would actually harken back to your question about the whole ChatGPT moment. And here's why. Because, there were language models before, and the culture was very different before that in all spheres, government, industry, researchers. People were not thinking in terms of a ChatGPT, a chatbot as being so impactful. Once that moment was shown, then there was a whole bunch of impetus towards how do we integrate this, how do we support these programs, how do we stay ahead of the world, so on and so forth. And so in some ways, that decision to take a language model, right, and even though it was by today's standards hallucinating like crazy, but the decision to go and put it in the hands of users to kind of have that ethos, maybe that's what companies can do. So I think the next company that goes and puts that out there, right, in the hand of the users, could be what robotics could do. Now, more tactically, that goes back to the other discussions the panel was having, which is what is the ChatGPT moment for robotics? One of the magic behind ChatGPT, why it was a ChatGPT moment, was every user could go and log in and share their input output, and within 24 hours across the world, everybody was sharing like how they prompted and what the outputs were. With the physical system, you don't have that quite, like, there was an answer earlier about enterprises and embodied AI, but in some ways if ChatGPT was quietly integrated into enterprises and it became like SAP, powering a lot of the world, but people don't know about it, it's not really a ChatGPT moment in the same way. And so I would, consider what is the ChatGPT moment for robotics. Part of Bolei's work, right, that he does, you see it very, very visibly when you get your food. People walking around see the robots going around. Maybe that bringing it to consumer is what we should try to do more than anything else. Just food for thought.
No, maybe actually, yeah. You make an interesting point. Maybe ChatGPT moment is not the right moment for robotics. I think I would probably call it the iPhone moment, because iPhone had that physical, a thing of beauty that you can touch and interface in a very intuitive manner, right? So maybe a robot that can actually, a cute robot that just like walks around the house and answers a few questions. Maybe that's the kind of like, I mean, I know people have tried this, like, as there was Asimov and bunch of well, smallish robots in the past, but I think I don't think they had the LLM power behind them. So with the help of all these latest technologies, I feel like maybe what it lacks is that interface, right? A beautiful interface, and maybe then that's equivalent to an iPhone moment, which will spark that next generation of apps on top of the robotic operating system. But any thoughts, Ashutosh? And maybe then I'll go to Pinder as well.
I think government can encourage collaboration passively. Government shouldn't interfere in businesses unless it impacts kind of basic protection of life and property. That's my view. But when it comes to consumers like DMV or FDA like drugs, that I think is something that government should regulate, because individual consumers can't fight or judge the reliability, and they have downstream effects of a car driving like crazy and hitting someone, or a drug going bad, right? But when it comes to business collaboration and encouragement, what we really need is more of a culture thing, that companies can work together, share data. There are committees that think about wireless standards. Government helped, but many of the wireless carriers really innovated and set standards that helped everyone. FCC now regulates that. So something like that could and maybe would happen in the area of robotics as well.
Yeah, I mean, Cisco has its roots in networking, and we built open and interoperable network of billions of devices with protocols that are standardized through bodies like IETF and entities like that. So I suppose, I don't know if like there are any such entities for robotics, especially if you have, I don't know, Coco Robotics interfacing with Torque AGI, interfacing with somebody else. I mean, there's no protocol that like sort of you can all talk to each other and sort of, I mean, in some sense, we are building the Internet of Agents, where agents are like, communicating over protocols like A2A and MCP and things like that. And we have actually, we've talked a little bit about semantic communication layers of the protocol stack to sort of facilitate inter-robot communication and stuff like that. So maybe some amount of like, open source, open standards around how these robots can actually communicate. One of the topics that we didn't touch upon in great detail is collaboration, right? Especially two robots from the same vendor versus robots across vendors. I mean, how do you actually even facilitate that? I mean, it's just, they barely talk to each other right now. I mean, extending it to like, robots coming in from completely different providers, completely different vendors. I mean, that substrate doesn't even exist. I think there's huge challenges there as well. But Upinder, I mean, any last thoughts on that? I know we
I'll
have like,
actually build on your point, and I think discussed this with Jayant previously, which was like, if you look back at these watershed moments in industries, for example, Android, right? Android is the same operating system, but now you have phones manufactured in the US, all over the world that are using it, right? So you build this familiarity with the end user who knows whatever device I buy, these are going to be the standard apps, and this is how I go about using it. AUTOSAR for automotive is also similar, right? Where you are basically standardizing all the common functions of a car, right? That goes into the stack, and then you're just kind of competing on the features that is in a particular model. That also takes away a lot of like the R&D that you might need to put into the software stack. And I am kind of waiting for that moment for robotics, right? So that sensors built in the US, sensors built in China or any other place, or robotic systems that are built anywhere else can all seamlessly work. Like I don't have to go and then program the entire SLAM stack for a different robot tomorrow. And that kind of meshing will make it very easy, I think, for the businesses because, like for example, a big Fortune 500 company can throw in the money to actually, build their own stack and own networking for their robots. But the generalizability is useful for much more smaller businesses, home environments, hospitals, and such kind, right? So if it's a much more standardized environment that they're operating in, whether it's from the human interaction side or their internal workings as well, I can then, be like, okay, I will learn this set of skills that I need, which is not like a full robotics expert, and then use these robots much more meaningfully for my work. So I think that is one thing that I am waiting for, and I think it will take in, like how all these things came about, even with Android, like a consortium of government agencies, manufacturers, industry, and even academia to work together to standardize the whole architecture in a way.
Thank you. This brings me to the last very quick segment, which is basically last final thoughts, rapid fire. I'll state the question and then just go in some random order. But what's the one major development or milestone you're working towards in the next 1 year? If you were to say 1 year later, if you were to maybe I'll invite some of you folks back to the Embodied AI Summit. Looking forward, like what would be that one major milestone? Maybe start with Achuta.
Yeah, trying to see if world models can help with the crowds effectively. You've got multiple agents, you don't know their actions, they're unpredictable. Can we have an embodied system navigate in crowds? And so this is work that we're doing with Jant. So hopefully a year from now we'll have some results, if not sooner.
Okay, Ashutosh.
We are really making the first steps in making the models better with physics. So as we go forward, the question becomes how we can take on more challenging applications and get our customers really on the front line at 99.99 with only hundreds of training examples.
Wow. Very cool. Upinder?
It's about integrating these perception stacks that I've been talking about and different perception modalities into existing VLA models and seeing how much more robust we can make them for the unstructured world. And that's also the work we're doing with Jant. So hopefully you'll hear more about it.
Thank you. Bolei?
Yeah, I will be excited to see the autopilot model we developed for sidewalk autonomy can be deployed on hundreds of boards and accumulate 1 million mileage.
Ooh, that's a big milestone. It's a very big milestone. Thank you. Thank you, folks, for very, very interesting and very deeply profound thoughts that you were able to share with us today. It's been a fantastic panel, and hopefully our audience also enjoyed the questions and the discussions and stuff like that. So that is a wrap from us. Thank you once again for tuning in, for everybody, and especially my heartful thanks to all the speakers and presenters and panelists for making this inaugural Embodied AI Summit at least a success in my view. I learned a ton, so I can take away with a lot of thoughts and lots of food for more research and more ideas. Yeah, so this is awesome. Thank you once again.
Thank you.